Good afternoon, everyone. Welcome to the second session of e-SMYIM 2020. I'll be chairing this session. I'm Sushmita Dash from the Mechanical Engineering Department at IISc Bangalore. I'll be chairing the session along with Professor Anand Govindarajan, faculty from IISc Bangalore. Anand, do you want to introduce yourself?
Yes, thank you. Yeah, thank you, Sushmita, for the introduction. I am Anant Govindarajan. I am an assistant professor in the Department of Chemical Engineering at IISc, and I work on atomic scale and quantum mechanical simulations of materials interfaces. So I'm very happy to be co-chairing this session with Professor Sushmita. And today our first speaker is going to be Professor Ashwin Joy from the Department of Physics at IIT Madras. And he's going to be talking about transport scaling laws in living turbulence. So I'd like to invite Professor Ashwin Joy to begin his seminar.
We have just a couple of minutes. So Ashwin, you could just like slowly begin the talk.
Yeah. So thank you, Sushmita. And I would like to thank all the organizers to consider me young enough to put a talk in this exciting meeting. I joined IIT Madras in 2015, and I remember vaguely giving the first edition, being in the first edition of Soft Matter Meet in Pondicherry. So since then, it has really evolved very well, and I've enjoyed all the editions of Soft Matter Meets. So thank you very much once again. Can I start, Sushmita, or should I wait for a few minutes?
Yeah, let's start. Let's get started. Yeah, it's already
Okay.
only 1 point.
All right. So good afternoon to all of you. I'm Ashwin Joy, working as a faculty member in the Department of Physics, IIT Madras. And today I'm going to be talking about some recent work that has been published in Physical Review F. I'll be talking about transport scaling laws in living turbulence. And this work was done together with research scholar Sanjay CP, who is working with me towards his thesis. This is Sanjay's first work. And in a nutshell, this is going to be the outline of my talk. I'll first give you an introduction of basically what active matter is. I'm sure a lot of you already know, but I'll give some general examples that will concur well with all our students who are attending this talk. And to describe, as it is customary, to describe any physical system, we need some governing models or numerical methods to study them in detail. So I will present the most popular model that is used to address these systems and the numerical simulations that we have used along with it. And towards the later half of my talk, I'll present some theoretical analysis that we have done to derive robust scaling laws that are valid over a large range of fluid friction. And I'll summarize my presentation with a few problems that we are currently interested in, and also they seem to be quite topical in this area. So active matter systems, as we all know, are systems that have perennial access to free energy. The constituent units that form an active matter system, seem to have a non-ending source of free energy, which results into a self-propulsion force, which I am showing here as a bold letter F. And this self-propulsion force is what that leads to flocking behavior in these systems. So typical systems that we are currently interested in is bacterial suspension at high densities. In fact, this is a system that directly falls into the purview of our theoretical investigation. This is a L. acidus bacteria, which is responsible for the proper functioning of our digestive system. It's called as the bacteria of the gut flora. And we are also, quite aware of fish swarms that are known to form, uh, these patterns that can be classified as flocking behavior. Bird flocks in the sky. We have all gazed, beautiful skies and seen these beautiful structures that are found by birds. And the last slide is actually a typical, you know, crowded suburban platform that you can see in some of the bigger cities of India. And from the scales of, the smaller scales in this picture is that of a bacterial suspension where the constituent units are of the size of few microns to the scale of, few meters. We have seen active behavior that leads to beautiful uh, patterns, self-organization behavior, so on and so forth. So the scales that are, you know, relevant here are quite wide, from submicron to the size of a few meters. And the interesting problems that one can find in this wide range of scales are many, and quite profound also. But we will be focusing ourselves, at least my group has focused itself on the smallest scale, which are the bacterial units that I showed in the previous slide. So before I describe, the constitutive equations or laws, I would like to pose some characteristics of these systems. So the independent units in these systems are, are what that leads to collective behavior in these systems. So, and these collective phenomena are very different from passive liquids. At low densities, these systems can show flocking. And here the ballistic transport, which is the short time transport, is shown to be dependent on density. Some works have shown that there are density or packing fraction dependent response in active matter transport. Not only that, the self energy, the free energy that is responsible for self propulsion has been shown to increase order at short range. So we know that most liquids, in fact, uh, it'll be it'll be okay if I say that almost all liquids exhibit a short range order. Okay, but self propulsion under certain scenarios can increase the short range order, which is quite non trivial if you think of it in terms of force acting on a single particle, and therefore of very great interest. In the high densities, the ballistic transport that I had talked about becomes non-trivial. And in this regime, when you have when you're working with low nuts and numbers because you are at high densities, you can also look at low Reynolds number turbulence, where, as I'll show a little bit in a short while, the energy spectrum can lack an inertial subrange. So power spectrums of the energy spectrums in low Reynolds number turbulence exhibited by bacterial suspensions can be classified, as lacking an inertial subrange. So I'll tell you what is the meaning of inertial subrange in a little while. And the literature on both these low density and high density effects is quite extensive. So there are quite a lot of papers on this. I am putting some important review articles here. This literature list is by no means an exhaustive list, but the literature is quite extensive. All right, so I'll switch to the system of my interest, which is the L. acidophilus gut bacteria. And as I said in the beginning, the length scales of the constituent units is around few microns. Okay, and if I need to model fluid dynamics or turbulence at roll Reynolds number, we need a continuum model for the dense suspension. And the continuum model must have or essential characteristics. And I'm listing them here. These models must accept turbulence at low Reynolds number. Okay, they should have provisions for low Reynolds number turbulence, where we know that the inertial terms are anyway not dominant. And these container models should allow for general patterns of energy injection and dissipation. Okay. So traditional Navier-Stokes is found wanting in these areas. And whatever constitutive model one chooses should accommodate for different types of bacteria, whether the flow around the bacteria is extensile or contractile, in the sense that whether the bacteria is a puller type or a pusher type, the model should be able to accommodate these characteristics. So these are the essential traits that any constitutive model must satisfy before it becomes a candidate for governing the dynamics. And the set of equations that we have taken are well known. They are built from ground up, and it has been developed from the branch of complex systems and essentially taken over by John Toner and Yohai too, to add a few terms for injection. So this part of the equation is well known. This is a typical Navier-Stokes, except for the inertial term, which has a lambda naught term sitting here. The grad P term is usual. Then we have a linear term, which controls energy injection. Dissipation is taken care of with the aid of two terms here. One is a cubic nonlinear term. Another is a linear dissipative term, which can be perceived as hyperviscosity because it has a fourth order derivative of the velocity field. And finally, I'm putting a frictional term, which is responsible for dissipating at all scales. So this is the Ekman friction term. Alpha has the dimensions of 1 over time here, which is called as the Ekman friction parameter. And we are going to, since we are anyway at low Reynolds number, we will close this equation with the compressibility condition. The parameters here are taken as gamma naught, gamma 2, and beta, all greater than 0. Okay, the precise values are not important, and we are modeling bacteria that is, capable of pushing instead of pulling, and therefore for that we have taken lambda naught greater than 0. Details of these, this model is given in the paper by Wensink, quite well known in this area. So armed with these governing equations, we have performed direct numerical simulations, or DNS, on a grid of 512 square. And we simply throw n passive traces. These passive traces are particles that are merely advected by the flow. They go with the local flow. Okay, the flow here is the solution of the constitutive equations. So this is a typical snapshot that I have taken in the steady state, where we have a balance between injection and dissipation. And the black dots that you see here are essentially the passive traces or Lagrangian traces that merely go with the local flow. And the color map here shows the level of vorticity in the snapshot. So we have computed the diffusion coefficient of these passive traces, and what you see on the right hand side is a plot of mean square displacement as a function of time. So you can see that the mean square displacement, or MSD, has a typical ballistic behavior at low times, or small, at early times, and it has a, in some sense, it behaves as t to the power 1 at large time. So that is the onset of diffusive regime, and therefore there is a transition somewhere in between where the mean square displacement changes from t squared to t. So we call that transition point as a crossover time, tau c, and the inset shows a map of crossover time as a function of the fluid friction, alpha. And quite interestingly, this crossover time has a minimum in the Ekman friction. So to understand this minimum and also to quantify transport and arrive at scaling laws for the diffusion coefficient, we turn towards the relevant length scales and time scales in the system. So we are trying to do this problem in the spirit of Kolmogorov, aka K41, where relevant scales in a steady state and isotropic and equilibrium should be able to describe some transport properties. So the first thing we did was to see how turbulence is enhanced or mediated by, the transport is enhanced or mediated by turbulence. So there are two relevant time scales in our system. So the ratio of gamma naught square by gamma 2 is dimensionally 1 over time. So that is the growth rate of the instabilities. And another time scale here is coming as 1 over mod alpha. So which we call as damping or acceleration time scale, depending upon the sign of alpha. If alpha is positive, then 1 over alpha is a damping time scale. If alpha is negative, then 1 over mod alpha is a accelerating time scale. So these are the two relevant time scales in our system. And a necessary condition for developed turbulence can be arrived at by taking a ratio of these two time scales. Okay, so if the instabilities grow faster than the rate at which they are damped, then we will have developed turbulence. That's physically accepted. Okay, so the fastest mode grows in the system, and there are a lot of modes that are growing at various rates. And if these modes can grow at a rate that is faster than the rate at which energy is churned out by friction, then we will have a developed turbulence. So when this condition occurs, we have a well-defined steady state. And one can see that the necessary condition is trivially satisfied as alpha goes to 0. Okay, so this condition becomes stronger and stronger. And therefore, it is not a surprise that the fastest crossover happens at 0 alpha, when you have no Ekman friction. Because there is our condition for turbulence is trivially satisfied. But now we have to answer another question, which is the scaling law for diffusion coefficient. Can be knowing the properties of the fluid. By properties, I mean the friction and the values of gamma naught and gamma 2, which are merely parameters for injection and dissipation. Can I give scaling laws for diffusion coefficient? So it's quite a leap in terms of doing a microscopic study, but turns out that we can still do a dimensional analysis under a few conditions of, under a few assumptions and arrive at a scaling law. So what we did was we turned towards a recent paper by Bratanov, who have, predicted a energy spectrum for these active liquids. So this is the power spectrum of the energy. And you can see that at very low wave number, the exponential can be approximated as unity. So it's a power law at low values of wave numbers. And what we did was we extremized this power spectrum and obtained a K star. K star is a peak value of the value of K at which the energy spectrum peaks. And that scales as the parameter delta. And from this K star, one can construct an inverse, which is 1 over K star, which has the dimensions of length. And when we plot the energy spectrum in our of our system at various values of the Ekman friction, we see that it has no inertial range and it is characterized by a single peak. Now the peak is nothing but K star, from which I can construct a characteristic length scale, because 1 over K is a length scale, And this is nothing but the mean size of vortices that you see in this plot. So we have verified that the mean size of the vortices that you see here agree with 1 over k star. And therefore, it is an important characteristic length scale. And the movement of the peaks as a function of friction can also be seen from the scaling laws that are given here next to the figure. So we are able to explain how the spectrum moves as a function of friction. But we don't stop here, because now we have a length scale and I need to compute a time scale, which is the crossover time. To compute a time scale, I need a velocity scale, because that's now using L, V, and T, I can construct any other length scales, any other characteristic scale. And to derive a velocity scale, we turn towards the energy equation. So here I have simply taken, I've simply taken a dot product of the momentum balance with the velocity u, and we have taken a time derivative. So this is, as fluid mechanics will easily reckon, this is nothing but the energy equation. So we have taken a long and tedious energy equation and written as many terms as possible in the form of a divergence. Okay, so now if I take the assumption of isotropy, homogeneity, and steady state, which are reasonable assumptions, okay, then I can take the divergences to be 0, okay, by simply applying Green's theorem on the boundary, and rewrite the energy equation in the form of a statistically averaged equation. So now here the angular brackets that you see are averages in the ensemble. Okay. At this point, we invoke we are claiming that these quantities omega square and del square omega dot omega will scale as u square over L square and u square over L4. Okay, they're dimensionally substituted with their scales, because these are the relevant scales. If you go back to the figure here, you can practically see that beyond the peak on both sides, the energy falls by a couple of orders of magnitude. So practically all the sensational stuff is happening at this length scale, k star. So therefore, I have replaced these average quantities by their approximated by their scales. And when we substitute them back, we get a scaling formula for RMS velocity, or RMS speed, if you would like to say that. Okay. Now I have the velocity scale and length scale at my disposal. I can construct a time scale. The ratio will give a time scale, which is what we do. And I'm going to show the results in a short while. But before that, we are also interested in computing the diffusion coefficient.
So it's been about 21 minutes. Could we wrap up in the next 3 or 4 minutes? So we have about 5 minutes for questions.
Yeah, I'm very close to wrapping this up. So here we have computed the diffusion coefficient, which is nothing but the standard integral of the velocity autocorrelation. And in the diffusive regime, that is at times much larger than the crossover times, one can approximate the right hand side as twice u square times the crossover time, and the derivative will give me the diffusion coefficient. So therefore, if I compute the diffusion coefficient from simply the characteristic scales and compare the values with the numerical estimates, we see that the agreement between theory and simulations is quite fantastic. So here the points that you see here are the data obtained from simulations, and the straight line, the dashed line, are the predicted values. They fall on top of each other, showing that the agreement between theory and simulations is quite exact. And now I'll try to end my talk with a slide on future scope, which is basically extension of this problem to include concentration gradients, transport of proteins, and an effective thermodynamic description of these traces. So this is the ongoing work that we are seriously engaged in. That's the end of my talk. So thank you very much.
Let's all thank Professor Ashwin Joy for this interesting talk. So now, if there are any questions, you may please go ahead and ask. I see that there's a hand raised by one of the attendees, Sriram.
Can I ask one question? Oh, sorry. Can I ask one question?
Right.
Okay.
Okay. So, Ashwin, it's a good talk. This is Dilip here from IIT Madras.
Yeah.
So,
yeah, please. There's a question by Sriram. I think he is asking. Can I answer this first?
Okay,
Because
please,
I think
please, go ahead. Go ahead.
so. He's asked me about the meaning of perennial access to free energy. Well, this is a loose connotation. I agree, but for all practical timescales of your experiment, the particles have an endless supply of energy. For example, if you take patchy colloids and try to model try to see activity, well, as long as the patches exist, the colloids will show persistent motion in some direction. So the source of free energy is large enough to propel particles during the observation times of the experiment. So it is perennial in that sense.
Can I ask now?
Yeah, please, Dilip.
Okay. So, Ashwin, it's a good talk. I have maybe you have explained it. I just missed probably the point. See, when you talk about that Eggman friction coefficient,
Right.
and it's scaling with critical time tau c. What is the meaning of having positive friction coefficient and negative? I saw that is the friction coefficient goes from positive to negative when you go to that side.
Yeah. So when I take alpha as positive, it acts like a typical friction. It acts as a damping term, which will take away. It'll act like a sink at all length scales. So at every length scale, it will act as a sink. It will take away energy,
Correct.
like viscosity does. Okay. And if I take alpha as negative, then it becomes a source at all scales. So it keeps on injecting energy at every length scale.
So how you visualize it in a physical system? That's
Yeah, very good. That's an excellent question. In fact, it's difficult to realize negative alpha, right? Positive alpha one can. So negative alpha, in fact, there are some recent papers that we read, can be visualized as putting some nutrients in this bacteria system. So if you throw some protein molecules or agents which these bacteria will absorb and will show greater activity in terms of longer persistent motion, they simply act as fuel. So that is like injecting energy at all scales. So nutrient mediated bacterial suspension is like putting more energy in the system.
All right. Thank you.
Are there any other questions? I see a hand raised by Vijay Krishnamurthy.
Hi,
Please go ahead.
Yeah, thanks.
Yeah.
So this is just a comment about the negative friction term that was just asked by Dilip. So in the original Turner 2 model, I thought the coefficient of the linear term for U was something that was coming from the ordering of the anisotropic units that's typically there. And so therefore the coefficient being negative really means that there is a local ordering that is promoted.
Yes.
And not really something about energy injection there. So you think when in terms of simple Landau-Ginzburg pictures in statistical physics, that's a standard term below the critical transition.
The symmetry broken state at local.
Exactly.
Broken state at
exactly.
So
that has nothing to do with energy injection per se. You can have that even at equilibrium. No?
Okay.
Are there any other questions? I had one question. This is regarding hydrodynamic interactions, which a lot of people in colloidal scale simulations incorporate. Are those implicitly included in because this is a DNS simulation?
No, we have not included hydrodynamic. You're talking about the tracers or in the fluid model?
About the tracers,
No,
the
tracers.
particles, right? It's
Yeah, tracers are simply advected, with the flow. They're Lagrangian movement.
I see.
They simply move.
And the okay, got it. Okay, thank you. Right. Are there any other questions from the audience? Okay. If not, let us thank Professor Ashwin Joy again for this very interesting talk. I would now request the next speaker, Professor Nityanand Goswami, to share his screen, and then we can slowly get started.
So I will close the talk.
Yeah.
All right.
Thank you.
So I'm just.
Hello.
Yeah.
This is Nitya here.
We can hear you.
Yeah, I've turned on my video, and I guess I can
Right.
just share the slides rather than sharing the whole screen.
Yeah, you should be able to do that.
Okay. Is it visible?
Okay. Yeah, it is visible. So I can just introduce you and then we can get started.
Sure.
So it's a pleasure to introduce Professor Nityanand Goswami, who is from the Department of Materials Science and Engineering at IIT Delhi. And today he'll be talking about nanoscale tribochemical reactions and triboprinting via liquid dispersed molecular additives and nanoparticles. Thank you for being a part of SMYM, and I'd now request you to begin your seminar.
Thank you, Alok, and the chair of the session, and all the organizers for putting effort. And thank you for inviting me. This is the first time I'm attending this symposium, which appears to be very interesting. Of course, I work not particularly on soft materials, but I deal with soft materials in terms of dealing with molecules, liquids, and nanoparticles as a lubricant. So I am a tribologist. And the tribology is, I'm going to get to that in a minute. So when we do tribology, there are certain things in particular which are of interest to my research group, which is the reactions which happen at the interface. And from these reactions, we have come up with a technique which can do writing on surfaces, which is like a printing kind of technique, which I'm going to discuss. So let me talk about what is tribology before we get into the reactions and printing related discussion. So tribology in the broad sense is science and engineering of interacting surfaces, where we are looking at relative motion between two surfaces in contact. And when there is a contact, there is going to be friction between the two surfaces. Wear will happen, material will deform, and then some material removal will happen. And that's a very important subject in terms of application, because there's a lot of emission and a lot of breakdown and reliability issues happen in engineering applications. For that, we need lubrication. So tribology involves all this understanding of friction, wear, and lubrication phenomena. And if you look at the scope of tribology, it spans all length scales, ranging from earthquakes, where you have friction between tectonic plates, which leads to earthquakes, engineering components in cars or any other moving component you can think of has tribological problems. Data storage has tribological issues because there's a moving disk against a read-write head, and a lubrication is very critical there. And future devices such as MEMS and NEMS, where again contact between surfaces, friction is important. So what is actually difficult or challenging in this field is the scientific understanding of tribology. And why it is difficult, I'll discuss in a minute. So unless we really get the most efficient system in terms of reducing friction and wear and getting the best lubrication, we will keep losing a lot of energy. And in terms of energy cost, it is around 23% of the total energy we produce every year is lost due to friction and wear. And in terms of GDP, in terms of economic loss, it's quite significant, 2 to 4%. And in developed countries, it's even more because we have less efficient machines. So in terms of safety, energy efficiency, reliability, it's a very important topic. Now coming to nanotribology. So my group works mostly at nanoscale, looking at fundamentals of friction and wear and lubrication. And why nanoscale is important? Because when you think about macro scale interfacial phenomena such as friction and wear, the origin of friction and wear is coming from microscopic asperities or nanoscopic asperities. So these asperities interact with each other. So you never have full contact between two surfaces. It's always dominated by these small irregularities, or you also call it surface roughness and asperities. So these asperities interact with each other, and there is obviously forces acting between these surfaces. So that leads to friction and wear of material. So understanding the friction and wear and lubrication down to these asperity level is very critical in order to understand the physics of the problem, in order to understand what is happening at each of these individual junctions. And it becomes even more complicated when there is surrounding liquid or fluid or lubricants. So when these asperities interact, you have possibility of deformation of material, you have adhesion between the asperities, and you can have wear, means removal or damage or fracture of these asperities. It can drive chemical reactions, which I will talk about, because there is a fluid around it, and this fluid can have reactive species, which indeed commercial lubricants have. And then you have other effects such as fluid confined between two closely spaced surfaces that can also change the interaction between surfaces. So how do we deal with the understanding of individual asperity contact is using a technique called atomic force microscopy, which my group is heavily using for doing this kind of work. So the idea is to go from empirical approach, which is what most industries use. The tribology at the industrial research level is very crude. So they just use this, classical laws of friction and try to correlate everything with empirical equations. Our goal is to understand the physics of the problem. What is happening at these junctions? What kind of phenomena is taking place? What are the factors which are resulting in friction and wear, and how to control it down to asperity level contacts? So if you look at the tip of an AFM in a transmission electron microscope, it does mimic a single asperity. So end of the probe it's just 10-20 nanometer diameter and can be modeled as a half sphere. So one problem which we took up using this approach based on scanning probe microscopy is to understand how automotive lubricants work. And we collaborated with ExxonMobil to carry out this work. So the problem with automotive lubricants is that there is an additive which is used in the lubricant, and it's environmentally not very good because it has phosphorus and sulfur, which produces compounds which clogs the catalytic converter. So the emission of the from the tailpipe, it's uh, not what we want. The efficiency of the catalytic converter drops over time because of the clogging. So there's environmental regulation which is getting more and more stringent over time to reduce this concentration of these additive in the lubricant. So in order to do that, we have to find a replacement. But there is very little knowledge of how this additive actually performs, how it reduces friction and wear. Unless we find a suitable replacement which is superior to this in terms of reducing friction and wear, we cannot replace it. So when this additive is added to the lubricant, it reaches to the interface, which you see in this picture also. Here you have lubricant between the piston rings and the cylinder wall, and some kind of reaction happens. So this reaction is due to the severe stresses and temperature uh, which is there during the frictional sliding. But there is not much known about how this reaction happens, what kind of parameters are important for this reaction, kinetics of the reaction and all that. So this is where we use this nanoscale approach, because if you remember now the last slide where we showed the tip of an AFM which mimics an asperity. So now we can use asperity level approach to look at this problem, and that's what we did. So we took this AFM based approach, and the good thing about this technique is that you can use it in a lubricant. We used an automotive lubricant under which AFM was operated. And we took iron coated surface. We also use steel as well. And then there's a heater to get a temperature which is relevant for these applications, 100 degrees to 140 degrees. And then we did very localized sliding to see if we can visualize this chemical reaction, which is happening in presence of this additive, zinc dialkyl dithiiophosphate, which is added to the automotive lubricant. So this is a movie which I'm going to play. I hope it plays. Okay, so what we observed is that when we apply the load with the help of this probe, above a critical load, if sliding happens, there is going to be a film which forms on the surface or at the interface. So this is happening at a critical pressure. If we apply low pressure, nothing happens. So low pressure is used when we want to image this surface. So then we did this experiment over several sliding cycles, and then we kept on taking snapshot at low pressures and then stitched together to get this movie animation. So this is a real experimental result. So in this central square, which you're seeing, is a chemical reaction which is happening at high contact pressure. And that reaction leads to formation of this very robust film, which is derived from this presence of, it happens only in the presence of this molecule. So this is a tribochemical reaction because it's a stress-induced reaction in a sliding contact. So tribo means rubbing contact. So that is what leads to formation of this film. So we did this experiment for a fixed sliding cycle in a small regions. If you see these rectangular patches, so these rectangular patches are showing you the film formation, which is very minimal at low pressures, but as the pressure increases, you see the thickness of the film is increasing. And this is just nominal contact pressure, which we calculated using Hertzian model, assuming a half sphere pressing against a flat surface. And we see that there is a good correlation. As the pressure increases, you see film formation gets faster, means for a given sliding time, we get thicker film. So the reaction rate is increasing. And at very high pressure, you see the deformation of the film. So film gets damaged also, damaged in the sense you are deforming the film because it's a It's a glassy polymer-like material which is deposited over the surface. So it is quite robust, but it cannot survive at very high pressure. So from this data, what we did was we calculated the volume growth rate. So how much of the volume growth we get per unit time, and then we try to understand it in terms of reaction rate theory. So we assume that it's a chemical reaction. We use a very simplified Arrhenius reaction rate equation, assuming that it's an exponential function. The growth rate is varying exponentially with temperature. But we also have to take into account the stress, because as I showed you in the last slide, as the stress increases, we clearly see that reaction rate is increasing. So how to account for stress? So we assume that as the stress increases, the energy barrier is reducing. That's why the reaction rate is increasing. So if that is happening, we have to take into account the change in the energy or reduction in the energy barrier, and take into account the stress, which has to be multiplied by activation volume to get to incorporate in the model. So we assume that energy barrier changes or reduces when the stress increases. And then when we combine these two equations, we get the reaction rate in terms of volume growth rate, which is now a function of temperature as well as stress. So now we did independent experiments, where in one experiment we varied the stress. I already showed you the results of stress variation at a fixed temperature. And then in other experiment, we kept the stress constant and varied the temperature just to verify this model is valid or not. So first is stress variation. We looked at the images, and now I'm plotting the volume growth rate. So from the images, I calculated the volume of the film, and then per unit time, what is the volume growth rate. So when we fit this data, it looks like a good fit up to certain stress level, but after that it levels off. It doesn't fit. I think I lost the pointer. Yeah, so it doesn't fit in this range. And when we now correlate it with the images of the tribofilm, you can see that the film is forming, it's a stable film which grows on the surface. But when we get into this regime where it's leveling off, we can see clearly that now the film is starting to wear away. So when the film is going to wear away, of course, the volume growth rate will not show continuous increase, because now material is being removed. So this data, this fit, which is for the volume growth rate, will not fit in that regime. So which I believe this is the only technique which allows you to directly see the film growth, calculate the volume of the film, and then correlate with the directly with the images of the film, that whether wear is happening or not. So it's all in situ kind of approach, which makes it quite unique. So in terms of energy barrier, we calculated from this fit somewhere around 0.8 EV, and activation volume came out also to be of the order of atomic dimensions, which is a reasonable number, suggesting that it's a chemical reaction happening at the atomic scale. But beyond that, of course, we cannot tell which reaction is happening and what atom is binding to what. That kind of accuracy we can't get, but at least it is giving us a confidence that it can be treated as a chemical reaction, and we see it, we can image it, we can see the growth rate of the film, and we see that it's a very robust film. So it has to be a chemically bound film. Then we did a separate experiment where temperature was varied, and we can see that as the temperature increases for a given sliding time and for a given contact pressure, the volume growth rate is exponentially increasing with only variation in temperature. So thicker film at higher temperature. Again, we came out with very similar values of the energy barrier, which gives us confidence that yes, the model we use where stress and temperature should affect the growth rate exponentially is valid in both the set of experiment where we independently vary stress and temperature. So this was the first time a commercial lubricant has been studied at the nanoscale. So that was the sort of uniqueness about this experiment, and then that's how we got quite a good impact publication out of this. And then we started applying it. Of course, now we are doing it on non-ferrous materials. We are now looking at other additives. And one more thing which came out from this work is the printing. So now you can see that we can control the reaction by sliding a tip in a particular region at a particular stress. So if we do that, we can write patterns by just inducing stress in that local region. It is very different than dip and nanolithography, which you might have heard of. That is based on capillary action. But here it is tribochemical, which means you are applying shear stress and normal stress, and that is leading to deposition of the material. And this deposition of the material, whatever is deposited, is very, very robust because it is formed under very high stresses. So this is an example of a car engine oil additive is being used to write nanoscale pattern. So we can draw channels, and we see that by increasing the load, or that will increase the stress, you can vary the height by factor of 3, and the width has not changed significantly. So you are basically growing thicker and thicker pattern by applying higher contact stresses. So when this was possible, then we realized that why not try other additives, because now lubricant industries are also interested in using nanoparticle based lubricants and also nanoparticle based additives that can be used for writing pattern for many other applications like devices or functional coatings. So then we did that, but we found that if we use a nanoscale sharp tip, we cannot deposit nanoparticles because they are much bigger than the contact size. The contact diameter is few nanometers. And if the particle is bigger than that, then you cannot trap the particles and you cannot deposit it on the surface. You have to have much bigger contact area. So we modified the AFM probe and glued a hard sphere, which can be steel or alumina. We tried both. And then this is how the probe looks like after modification. We glued a sphere of steel, which we commercially obtained. And that gives us a contact diameter of 300, 400 nanometers, which is quite big compared to the size of the nanoparticles. So once we do that, we can now trap nanoparticles at the contact. And once that happens, these particles will be stressed due to this probe applying of the order of a gigapascal pressure, and then we shear it, and then we can actually deposit a film out of these particles. So we managed to do that, and you can see that pattern forming on the surface. So this is line pattern. We drew a rectangular region where we did raster scanning, so we can deposit different types of patterns. And of course, stress, if you apply higher stress, you get thicker film. So this was zirconia nanoparticle, which was deposited. So this was the first of its kind work in terms of tribo stress induced printing. So it was published in 2018. And then we patented it also, which patent got granted this year, just a few months ago. So you can see very, very dense film is forming. Nanoparticle is not at all can be identified. It is completely fused. So such kind of high stresses are there, which gives you very, very robust film and highly crystalline film. And then we also realized that the capping agent which was used to disperse the particle was not present. We did chemical analysis of the film, and we see that that is completely removed because of the stresses. And that's why particles can fuse also, because this organic capping agent was completely gone due to shear. So how much time we have still?
You should finish in maybe 1 or 2 minutes, because then we'll have like 5 minutes for questions.
Yeah, I'm coming towards the end. Okay, so then next thing we did that we now try to mix different additives. Like we can mix two additives together. So we added this ZDDP with nanoparticles, and then we deposited layer by layer film. And then we can also do composite. We can have two different types of nanoparticles or one molecule which reacts with the substrate with another nanoparticle, and then we can have a hybrid composite film. So this kind of novel, nanostructured film can be deposited using this approach. So with this, I'm coming to the conclusions. So I demonstrated that tribochemical reactions can be visualized with very high precision using single aspirity contact in an atomic force microscope. We can see these reactions happening live. We can image the film which is growing on the surface, and then we can understand the kinetics of the growth. We can see how different parameters affect these reactions, like stress-induced growth rate we analyzed. And then we can do printing of nanoparticles using large contact area using a colloidal probe. So, so this approach, we are now trying to address, trying to make new novel coatings, and also trying to address problems relevant for lubrication industry to reduce friction and wear, and understand these tribochemical reactions which are relevant for lubricant applications. So with this, I would like to end here, acknowledge my previous collaborators, current collaborators, previous organizations where I worked, and current affiliation and the funding source. And thank you all for your time. And I will be happy to answer any questions.
Let's all thank Professor Nityanand Goswami for his interesting talk. I'd now like to invite the audience to ask any questions.
Can I ask a question? Oh, sorry.
No, Dilip, go ahead, please.
Okay. Hello, Nityanand, it's excellent. Very nice talk. I have essentially two questions. The first question is that when you talk about the zirconia particles getting attached to the surface, basically embedded by force, or they are some sort of adhesive force that keeps the particle attached? What is the interest?
It is not adhesion, because adhesion can, because we have tested the scratch resistance of this film. We have actually, if I go back, my slides are visible?
Yes, I can see.
Okay, my keyboard somehow is frozen. Let me see. I want to go back. It's not allowing me to go back. Let me just. So if you look at the TEM image of the cross section, FIB cross section, if you look at the interface, it's completely fused.
Yeah.
So there is like atomic scale diffusion at the interface, because interfacial diffusion will be, interface will be very active. So when you have these stresses, atoms will sort of interdiffuse and weld. It's like a cold welding because of the high stresses. And you see all the particles are you can't recognize individual particles in this high resolution TEM image because they are fused together. So it has formed a polycrystalline film, and this center is, we call it tribocentering. It's a well-known phenomena in macro tribology. People do look at.
Essentially, it's a buried layer. It's essentially buried layer where the particles are embedded into the surface.
It's like a sintered product you are seeing.
Okay. I have a second question, just quickly. See, usually what happens when you have this colloidal probe tip, and you have a fluid in between a surface and the tip, depending on the distance between the colloidal probe and the surface, there are some reports of this integer and fractional layering of fluids, and that will
this layering, right? Layering
of fluids.
My whole PhD was on layering. So looking at
those forces in this case.
But those forces are extremely weak, and here we are talking about applying a gigapascal pressure. So those layers don't survive, and the kind of stresses we are working, and those layers, first of all, you need very flat surface to see those layers. Otherwise, they are going to be very, very weak because they get disturbed if you have rough surface. And these are very rough surfaces. We are looking at,
I see.
polished steel. We are not looking at mica flat surface or graphite flat surface. There you will see very strong layering. And my whole PhD actually was on that topic.
Okay,
So,
nice to know. Okay, thank you.
There are a few questions from the audience. So Sriram has posted, he's asking what is activation volume and if there is a reaction product deposition on the AFM tip.
So yeah, it's a both questions are very good. Activation volume is like a virtual volume. People use it for modeling this stress activated reaction. It's physically, I mean, people say that if you, I mean, it is kind of a volume where likely this reaction is concentrated. So if you're talking about atomic scale reaction, this from the fit, the number you should get should make sense that it's an atomic scale reaction. It should be of that order. So from our results, we got activation volume of the order of 4 or 5 angstrom cube, which makes sense in terms of which is reasonable number to say that it's an atomic scale reaction. But it's actually not. It's a virtual volume. It's just a model. There's no real exact. You can't correlate with exact volume of certain particular atom or species. It's like a virtual volume where we assume that that's where the that's the volume in which reaction is happening when you apply stress. But yeah, I don't know beyond that. I'm not a theoretician. So if there is a theoretician who wants to chip in and say more, I would be happy to get their views as well.
There's another question by Dikshit, which says, can you comment on slide 7, why peaks are higher at the edges and mostly on the right side?
So that's due to deformation of the film, and it's due to asymmetry of the tip. So when you slide tip left and right, if you may have more pressure on one side if there is a asymmetry in the probe. So that's why there is a more stress acting when you slide in particular direction. So it's not uniform in both the direction. That comes from the asymmetry of the probe. So stress is more when you are sliding in either left to right or right to left, depending on the shape of the tip. So if you have a uniform spherical probe, then you are right. It should be, the material deformation should be uniform on both the sides, but we don't see that, and we believe it is due to the asymmetry of the probe. One more question I missed, which was if there's a tribofilm forming on the probe or not. So that question, actually, sometimes we see that, but in sometimes what happens, the probe wear happens because it is continuously sliding at very high stresses. So if the probe wear, which is actually few nanometers per hour, even that kind of small wear will lead to will prevent any tribofilm forming on the tip, because tip is gradually getting worn over time. So we see that chances of forming film on the tip is very less because the tip itself is wearing, although at a very low rate, but it is wearing over time.
Right. In the interest of time, I think we should stop here. So Sriram, I would encourage you to contact Professor Nityanand Goswami by email. He has one more question, I think. So that
sure,
can take place.
please.
So thank you, Professor Goswami, for your very interesting talk. Our next speaker is going to be Professor Jason Picardo. He is coming from the Department of Chemical Engineering at IIT Bombay. I'm very pleased to welcome him. Thank you for participating in SMYM, and please, we are looking forward to your talk.
Thanks a lot for the introduction. I'll just share my screen and get started. Okay, so I hope my screen is visible. Let me know there are any issues.
Yes, it is visible.
Okay, so good afternoon. It's really a pleasure to be here and participate in this meeting and to have the opportunity to share some recent results on the mechanical scission of polymers as they are transported in a turbulent flow. So this work has been done in collaboration with Dario Vicenzi at University Côte d'Azur, Shamridhi Shankar Ray at ICTS, and Takeshi Watanabe at Nagoya Institute of Technology, Japan. And I'm thankful to funding from the IIT Bombay seed grant. Okay, so the broad interest in understanding polymers and their impact on turbulent flows stems from the fact that even a small amount of polymer, even in ppm amounts, can dramatically reduce the drag in a turbulent flow, for example, in a pipe, or equivalently the rate of dissipation of a turbulent flow if one considers the more theoretically amenable case of homogeneous isotropic turbulence. And so this kind of Tom's effect or the drag reduction effect, it owes its origin to the fact that the polymers can be stretched out by the turbulent flow, because these stretched polymers, when they relax, they exert feedback forces onto the flow, which modifies the flow and is ultimately responsible for reducing the drag. But the catch is that the same stretching can also ultimately lead to the polymer breaking up, simply because the force exerted on it exceeds the strength of the bonds. And this was recognized quite early, as seen here in this very nice visualization from a paper in 1993. So what they plotted here is they've done experiments with polymer solutions of polyisobutylene in turbulent pipe flow at different concentrations, and plotted the classic friction factor plot versus the Reynolds number. So basically this shows you the drag as you do experiments at different Reynolds. The curve on top marks the Blasius line, which gives you the drag in a Newtonian flow. And the bottommost curve is the maximum drag reduction achievable according to Works asymptote. So you see the symbols show you the results of the experiments. And the concentration is enough to get you the maximum possible achievable drag reduction. But what you note is that as you increase the Reynolds number, there comes a point where you ultimately start increasing in drag again, or you lose the drag reduction effect. And this happens because the polymers start to break up. So if a polymer breaks up, essentially you get daughter polymers which have lower molecular weights and therefore are less amenable to stretching. Or in other words, they have shorter relaxation times. So these smaller polymers can no longer be stretched, and so you lose the drag reduction effect. And here you see that if you start with more amount of polymer, you ultimately can, go to larger Reynolds numbers, but ultimately the breakup rates are so large that you can't keep up and you lose the drag reduction. Now, this is an experiment where you have a fixed residence time. A situation that's closer to what I'll be looking at today is the following experiment in a kind of mixing container done by the group of Suarez et al. And what they do is, you basically put the polymer solution, you stir this mixture and you measure the drag. But now you can monitor the drag reduction versus time, because you can keep this solution in this box as long as you wish. And so these are some results from their paper for different polymers at a variety of Reynolds numbers. And what you see in each case, there might be some transients as the polymers begin to stretch and exert themselves, but ultimately you reach a peak in the dissipation or drag reduction before you then slowly start to lose this effect. And this slow but certain loss is due to the scission that we want to understand, and I'll try to talk about in today's talk. Yeah, so when it comes to modeling polymer scission, both experiments and theory have progressed quite a bit in the case of laminar flows aimed at geometric devices or at studying individual polymers like DNA strands and so on. And they're typically a Brownian dynamic simulation is a useful tool because the flow is just a simple linear background flow. And so you can do these kinds of simulations, especially with today's computing, quite easily. On the other hand, when it comes to turbulence, experiments have been more recent, but now there are actually quite a few studies like the ones I just showed you. On the other hand, there is a complete dearth of modeling studies, and as this has been noted in the recent review by Suarez in the Journal of Non-Newtonian Fluid Mechanics. So it's really quite an important open question to model accurately scission and its impact on drag reduction and other associated phenomena. So the reason this remains challenging is because continuum models cannot account easily for scission, right? Because scission occurs at the molecular level and it occurs really as an extreme event. So when the polymers get stretched, to their largest extent is when it breaks. So if you want to account for scission, you have to account for something that's at the end of the distribution of extensions. Whereas continuum models like Fene usually describe, or Fene-P, usually describe the kind of mean of the distribution. So this remains an issue, and also scission depends on the entire strain history or the Lagrangian history of the polymers. So in the work I'm going to show you today, we are going to combine Brownian dynamics or bead spring simulations for polymers along with direct numerical simulations of the Navier-Stokes equations. And what this allows us to do is it allows us to enforce a precise condition at the at individual polymer levels, and then allows us to understand the detailed statistics of scission. And our hope is that eventually these studies will lead to a framework for closures for Olroyd B or Fene-P type models. Okay, so a brief outline of what I'll be discussing in the next few minutes. So first I'll take you through quickly the bead spring model we used, as well as the background turbulent flow. I'll then first talk about passive polymers, which are basically a situation where you have a very dilute suspension, so you can ignore feedback effects. And we just focus on how the polymers are broken up by the flow. I'll take you through some analytical results and then compare that with simulations. I'll then look at polymers that are concentrated enough to feedback on the flow, and this will allow us to directly see how dissipation reduction is impacted by scission. And then finally, I'll look at the situation. I had not mentioned this earlier, but the previous two cases, we will look at only the first scission event, but then I'll finally also look at how multiple scissions affect the dynamics, wherein an individual polymer molecule can break up repeatedly until it reaches some really small fragments that are inextensible. Okay, so today we'll be considering these polymer dynamics inside a homogeneous isotropic turbulent flow. So to generate the flow, I solve the Navier-Stokes equations in the three-dimensional cube, where I have a forcing term F that injects a fixed amount of energy per unit time into the flow in the large scales. And this energy cascades down through the flow due to nonlinearities and a la Kolmogorov, and ultimately it gets dissipated at the Kolmogorov scale due to viscosity. So such a flow can be characterized by a large scale which corresponds to the forcing LF, and a small scale at the dissipative, the dissipation scale eta, which is the Kolmogorov length, and an associated time scale tau eta. Now these quantities can be defined by Kolmogorov phenomenology and the energy cascade in terms of the kinematic viscosity of the fluid and the mean volume averaged dissipation rate, epsilon bar. But if you look at the dissipation field over space and time, it's actually quite intermittent, as you see here in this cube. So this cube shows you a visualization of the regions of the flow with extremely high dissipation. So blue is highest and yellow is a little milder. And you can see it's kind of clumped up intermittent and as this kind of sheet-like geometry. Now this is important because the dissipation is directly proportional to the norm of the symmetric part of the strain rate of the velocity gradient tensor. So really these blue regions correspond to regions of the flow where there's a very large strain rate. So you can imagine a polymer moving through this fluid experiencing large fluctuating strains, which is what is seen here very nicely by these simulations by Watanabe and Goto, who were the first to simulate bead spring polymers in a turbulent flow. So you see, if you just focus on the red curve here in the inset, it shows you a time trace of the dissipation or the strain rate equivalently of a Lagrangian particle or a tracer that moves in the flow. So you can see the spiky intermittent nature of the strains that a polymer would get subjected to. Now, final point about the flow is that the flow, of course, is chaotic and chaotic in a Lagrangian sense. So if I put two particles close together in the flow, they tend to separate out exponentially on the average with a time scale which is the inverse of the Lyapunov exponent lambda. And this Lyapunov exponent is about 0.15 times this inverse Kolmogorov time. So basically, we have this number for our flow. And this is the most appropriate scale to use to define the Weissenberg number. Because you can imagine if you take a polymer like a dumbbell, its beads will get stretched out exponentially with this inverse Lyapunov exponent. And so we take its ratio to the relaxation time of the spring to get a Weisenberg. Okay, so this is my polymer model. I'm using the classic Rouse model here to start with, the free draining chain. So the center of mass just moves with the fluid velocity with some diffusive contribution from Gaussian white noises that are imposed on the beads to mimic Brownian thermal noise. When it comes to the separation vector dynamics, QI, you see that the links between the beads are stretched out by the flow due to the local velocity gradient, and it's counteracted by spring forces. And here I use Fenner springs, so I have a maximum spring length QM. An important thing to note is that this flow stretching can be captured just using a first order Taylor series expansion, even though the flow is turbulent. This is because the polymer molecule is sub-Kolmogorov or smaller than the Kolmogorov scale. So locally it experiences a linear flow, but in time that linear flow is fluctuating according to its motion through the turbulent flow. Another important thing to note in the model is that one can relate the time scale of relaxation of an individual link to the overall relaxation time of the entire chain via this mapping, which was introduced by Jin and Collins in 2008. And you can see here that if tau is the relaxation time of a link, the equivalent relaxation time of the overall chain, if it were represented by a dumbbell, tau d, is much larger. Which makes sense. So if I take the same kind of microscopic links and I join them together into a larger chain, the object has a longer relaxation time and is more stretchable. And so I use the effective relaxation time to define my Weisenberg number by multiplying with the Lyapunov exponent. Okay, so before I move on to scission, it's instructive to revisit ideas of coil stretch, especially in turbulence. So the coil stretch idea is well known in laminar flows, where basically here I'm showing you now the probability distribution of the extension, so the end-to-end separation of a 5-bead polymer chain in a simple bi-extensional flow. And you see that the distribution is highly peaked about the mean, and as you increase the Weisenberg number, the peak simply shifts to large extensions. On the other hand, in a turbulent flow, if you have a small Weisenberg number shown by the red curve, you basically have a peak about small extensions. But as you increase the Weisenberg, the polymers extend out, but the PDF behaves very differently from the way it does in a laminar flow. Instead of the peak shifting, you actually get a very broad distribution, which then, when you have the coil stretch transition, the peak just shifts from the very small extensions to the maximum extension. This is shown more clearly in this log scale plot, where you see that there are really broad distributions in extensions as you increase the Weisenberg number. And this is why studying scission in turbulence is quite different from doing it in laminar flows. Because the polymer is experiencing this fluctuating strain rate, it has a really broad distribution in its extension. So even if you have a relatively small Weisenberg, the tail of the distribution is so large that you can still have non-negligible scission events. Okay, so the final piece of our model is, of course, to model the scission event itself. So now at its very basic level, scission occurs when the force exerted on the polymer molecule exceeds a threshold. And in our context of our Fenner chains, the force on a link can be invertibly related to its instantaneous length. So we basically have a scission criteria on the length of the link. And so in our simulations, if any of the links of our chain exceeds a prescribed threshold, LSC, or the scission length, we basically break that length and we count that as a scission event. And when I study multiple scissions, I break that length, but I continue to follow the two remaining pieces, which I call daughter polymers. And in our simulations, the scission length is fixed to be 80% of the maximum length as per the Fenner spring law, but that detail doesn't really matter and doesn't really affect the results. So it's important to point out that you can have more advanced models of scission, but as a starting point, the bead spring chain and this simple criteria is very useful, and it captures the basic physics. And I'll try to also tell you how hydrodynamic interactions and extruded volume interactions enter the picture later on. So quickly, before I show you numerical results, it's interesting to note that one can derive analytical results if you make a certain simplification. So you just consider a dumbbell model with a Hookean spring, and then you replace the turbulent flow with a random stochastic so-called Crichton flow. This then allows you to derive a Fokker-Planck equation for the probability of the extension of the polymer, where now the direction doesn't matter because you assume, you are in an isotropic situation. So this is the Fokker-Planck equation for this flow where the diffusive and advective coefficients depend on the Weissenberg number and on the noises via the equilibrium lengths. And the boundary conditions are reflective at the origin, and to enforce scission, you put a sink boundary condition at the scission length. So that's what enforces scission. Now, this operator with these boundary conditions actually has orthogonal eigenfunctions, which is very useful because you can write down the decay rate. So the number of polymers surviving in my simulation, NPT, to the original number of polymers is basically the integral over all lengths of this probability distribution. And because this probability distribution can be decomposed into eigenfunctions, I can just take the slowest evolving mode to get the kind of decay rate of my number of polymers. And so this simple analysis shows you that the number of polymers would decay exponentially with a time scale that comes from that eigenfunction. Okay, so let's now look at some numerical results. So you see, so in our simulations, we've defined the Weissenberg number such that the coil stress transition occurs for a Weissenberg number of 0.5. So on the left, I'm showing you how the number of polymers evolve in time for different Weissenberg numbers. And you see this clear exponential decay on this log linear plot. And from these curves, of course, I can extract the decay time TD. Equivalently to this, I can also measure the time it takes a polymer to break, or the scission time, or in other words, the survival time. And that you see corresponding to the figure on the left, it shows you exponential tail. So it behaves like a Poisson process with another time scale gamma, or gamma inverse. And so I can extract TD and gamma from both these plots and plot it as a function of Weissenberg. And you see that as you go through the coil stress transition, there's a dramatic decrease in the time decay time, as well as in the time scale of the survival. And so those things actually correspond to each other. The green and the red curves overlap here. So the time scales of this tail as well as the decay are the same as may be expected for such processes. So the important thing to note from there is, as you cross the coil stress transition, you have a dramatic increase in the rate of breakup, as may be expected. Another thing that our simulation allows us to measure is which link in the polymer chain is broken. So it's well known from both laminar and early turbulent studies that scission occurs at the midpoint of polymers. And so we try to measure whether that occurs in our simulations as well. So you see that if I look at a relatively low Weissenberg number of 1 and I plot the histogram of the locations where breakup occurs, you see that most of it occurs at the middle. So here I'm looking at a 10-beat chain, so I have 9 links. And you can see that most of the chains break up at the center midpoint. So this confirms the midpoint scission scenario that's well known in the field. But if you increase the Weissenberg number, what you see is that at large enough Weissenberg, you have a more broad distribution of breakup locations. And so you have more chains that are breaking up, like in maybe 3:4:1/4 ratios and so on. So this means that the ultimate distribution of daughter polymers you get after spending some time in a turbulent flow is going to be broader. The molecular weight distribution will be broader. So now, before I leave these passive polymers, let me quickly talk about the role of hydrodynamic interactions as well as extruded volume interactions. So to do this, I go back to the Rouse model and include HI interactions in the standard way using the RPY tensor. And I also, so this basically means that I'm accounting for the forces experienced by a bead due to all the other beads in the chain. I also account for extruded volume interactions with a simple Gaussian repulsor potential. And this shows you a typical result. So the red curve corresponds to my free draining Rouse model chain. The green curve shows you the effect of only hydrodynamic interactions. And the blue curve shows you HI plus extruded volume. And what you see is that hydrodynamic interactions tends to delay breakup, whereas extruded volume counteracts that effect to some extent. Now this role of HI can be understood if you look at a time trace. So I'm looking here at the evolution of the separation, end-to-end separation of the polymer. So you see that in the case with hydrodynamic interactions, there is less of a tendency to undergo large fluctuations about its original starting size, which I have taken to be the equilibrium size. So basically what this tells us, and this is kind of well known in the field, that if you start with a coiled polymer, hydrodynamic interactions kind of shield the polymer and make it harder for the polymer to uncoil in a flow. And therefore this kind of delays the scission process. But on the other hand, extruded volume tends to make the polymer separate out, and therefore that you have this compensatory effect.
It's been about 20 minutes, so if you could finish in the next 2 or 3 minutes, that would be great.
Sure, thanks. So quickly, if I move on now to active polymers. So here I am accounting for the fact that polymers are feeding back on the flow. If I plot the decay rates versus time, the thin lines correspond to passive and the thick lines correspond to active. You see that at long times, the active polymers behave like passive polymers, but at the short time, there is a slower kind of decay rate. And the reason lies in the fact that the active polymers, or by active, I mean they are able to feed back onto the flow. So these active polymers actually reduce the dissipation, as can be seen here. So I plot dissipation rate with time. And you can see that the actual Newtonian value is 0.5. But when you start with the polymers, there is a dramatic reduction in dissipation, which then is slowly lost as the polymers break up. So it's because of this evolution of the flow itself that the dissipation is lower at the beginning, which is why you also see lower scission rates. But ultimately, when you recover the Newtonian regime, you basically start behaving like passive polymers. Another important thing to note from this dissipation plot is you can see that the large Weissenberg number has the strongest initial reduction in dissipation, but it also loses that effect very quickly because large Weissenberg polymers break rapidly. The smaller Weissenberg case, the red curve, has a lower initial dissipation reduction, but that effect survives for much longer because its dissipation rate seen here is slower. So clearly there is an intermediate Weissenberg number which kind of optimizes your time integrated dissipation. And that's one important outcome and something that these simulations can help quantify. Okay, so the last thing I would like to show is what happens if you follow a polymer molecule and account for the fact that it breaks up subsequently and repeatedly. So that's what I'm showing you here. I'm now taking a bunch of polymers and I'm going to plot the number of surviving polymers of different sizes shown by the number of beads n versus time. So you see that at small Weissenberg, only the 10 bead chains break and many other beads, many other daughter polymers form, but they just remain constant in time, they don't break. But as you increase Weissenberg number, you see more of the daughter polymers break. So for example, at Weissenberg 2, a 5 bead polymer starts breaking. Whereas if you go to Weissenberg 4, almost all the daughter polymers break except for dumbbells and even 3 bead polymers have a slow breakup rate. So we can understand which of these guys break and which do not by using the original mapping I told you about, and we just compare the overall relaxation time of a daughter polymer to the parent relaxation time. So you have this relationship between the Weissenberg of a daughter polymer and the Weissenberg of the parent polymer in terms of the current number of beads and the original number of beads. And so if you compare that to my coil stress transition and you say that if your daughter polymer has got a Weissenberg less than the critical value corresponding to coil stretch, then that polymer will survive. And that is enough to explain these results, although I won't go into the details. It gives us a good guide to know for a given Weissenberg number, which of the daughter polymers will break and which will survive. So that brings me to a point where we can now make a comparison with experiment, and I'll wind up with this. So essentially the largest polymers that will survive in a turbulent flow are the daughter polymers whose Weissenberg, like I said, is just below the coil stress transition. So that condition is basically here using Jidden-Collins mapping. So this is basically the time scale of the daughter polymers, just less than what's required for it to break. So what this means now is I can relate the number of beads of the daughter polymer in the case of a large number of beads, n square, to the ratio of the Kolmogorov time of the flow to the relaxation time of the polymer. But I can relate the Kolmogorov time of the turbulent flow to the Reynolds number, as I had shown you at an earlier slide. And so we get a scaling relationship if we make the connection between number of beads to the contour length or the molecular weight of the polymer. that L square, the contour length squared, goes as a Reynolds number to the -3/2. So this is what comes out of our simulations and a few simple considerations. And this actually jives very well with the experiments by Shiva Vanapalli and co-workers in PNES way back in 2006. So they did a bunch of experiments in different rheometers, but under turbulent conditions. So you had cross slot, contraction, expansion, and rotating kind of geometries, rotating disk geometries. And in all cases for different polymers, they obtained the same Reynolds to the -3/2 scale. The dashed line shows you what happens in laminar flow, so you can see it's clearly turbulent. And secondly, you can see that for different geometries, you obey the same scaling. So this shows you that at least in their experiments, the geometry wasn't important because most of the breakup was happening in the bulk, where the conditions are roughly homogeneous and isotropic, which is why our simulations are able to explain this scaling. Okay, so with that, I'll conclude. Possibly the main take-home message from this talk is that drag reduction or dissipation reduction owes its origin to polymer stretching, but its demise to polymer scission. And so therefore, there has to be an intermediate Weisenberg, which does stretch enough to give you drag reduction, but not so much that it breaks quickly. It's important to note that such considerations of scission would also be important at the low Reynolds number elastic turbulence regime. But here the turbulence itself will decay along with scission, whereas in Newtonian, whereas in the high Reynolds number turbulence, you actually recover stronger turbulence. So this elastic turbulence problem is something that's interesting to consider in this light of polymer scission. And finally, there are a whole range of avenues open for work now, which require modeling and comparison with experiments. That includes, looking at more detailed polymer models, but also looking at more complex turbulence problems or turbulent flows. So with that, I'll skip these things in interest of answering questions. And so I thank you for your attention. This work is in press with JFM and will hopefully come out soon. So I'll be very happy to take questions. Thank you.
Let's thank Professor Jason Picardo for his very interesting talk. There's time for one quick question from the audience. Yeah, go ahead.
Hey, Jason, can I ask you a question?
Yes, hi. Yeah, sure.
Yeah. Hi. This is before you started your talk. I don't know the field quite well. So this, when you showed that there was a drag reduction that was measured, one of the plot where drag reduction was on the y-axis and x-axis was something. So how was it defined and how was it? Because you showed an experiment where they had a concentric cylinders and just
right. So. Okay, so basically the first plot was just the friction factor plot. So you have the turbulent flow in a pipe and you measure pressure drop and versus the mean velocity, and then you kind of get the friction factor from the pressure loss, and you plot that versus the Reynolds number. So this is like the Moody friction factor chart kind of thing. So here what you're really measuring is pressure loss, and when you put polymers, the pressure loss reduces, and that's what they are kind of quantifying here. In the drag reduction, I believe, in the second experiment, it again has to do, I think, with the amount of power or torque that's applied to drive a certain velocity in the flow. And what you will see here is when you put the polymer to maintain the same kind of mean flow speed, the amount of power input required will reduce. So in that sense, you can kind of backtrack the drag.
It's the ratio of something with the polymer and without the polymer.
Exactly, yeah. So you kind of measure the power input to the output kinetic energy of the fluid and call that a drag, and then you look at how that varies with addition of polymer, and then of course with time to get the scission effect.
Yeah, great.
And in my simulations, I can directly calculate the dissipation from the flow.
Okay, yeah. Thanks so much.
Sure.
Let's thank Professor Jason Picardo. Thank you for your very interesting talk. And actually, time for the last talk in this session, and I'm actually going to be the speaker for that talk. So I'm going to go ahead and share my screen. Right. I hope you can see my screen.
Yes, we can.
Okay, excellent. So my talk is titled the role of electrostatic interactions in the wettability and frictional properties of heteropolar two-dimensional materials. And the talk primarily deals with two-dimensional materials, which are materials that have a layered structure and can be exfoliated into thin sheets up to a monolayer. So you would have heard of materials like graphene, right, which is just a layer of singly bonded or triply bonded, sorry, carbon atoms. So every carbon atom is connected to three other carbon atoms. This is a hexagonal pattern which kind of repeats, and these layers of graphene, they're held together by weak van der Waals forces. So you can exfoliate them up to a very monolayer or single layer of atoms. And this material is semi-metallic, and it is actually homopolar because it consists of the same set of atoms inside the entire material. It has a very high Young's modulus of 1 terapascal, given how thin it is. Now, given that at the bulk scale or in the macro scale, there are semiconducting, metallic, and insulating materials, the same kind of diversity is also found in the nanoscale. So materials like hexagonal boron nitride, this is an insulating material compared to graphene, which is semi-metallic, and it's actually so there's some nitrogen atoms and some boron atoms, and because of the difference in their electronegativities, there is some potential for the electrostatic interactions in the material to bring about some interesting physics. And you can also have semiconducting materials, for example, molybdenum disulfide, which basically consists of one layer of molybdenum atoms being sandwiched by two layers of sulfur atoms. So every layer of MOS2 is basically a trilayer. This again is a heteropolar material, so you can think of interesting physics coming up. And the kind of applications we want to use them is in flexible solar cells due to their optoelectronic properties. You can think of creating small holes or nanopores in these materials. Thereby, you can use them as barriers or as membranes for desalination or gas separation. A lot of experimental work is actually coming out in this area. And finally, because of their high activity at the edges, you can think of using them as catalysts for several reactions. So in many of these reactions, the material comes into contact with liquids. So those are the kind of applications we are interested in. So these are solid liquid interfacial applications of 2D materials. I'm just going to quote a few representative examples here. For example, in desalination, of course, water and ions, aqueous solution will come into contact with the 2D material, which will have a nanopore for salt separation. And then if you do something like oil water separation, which scientists have done before, again, liquids are coming into contact with the surface. DNA translocation is another application where you have aqueous solutions coming into contact with the 2D materials. And finally, there have been some reports of using the opposite process of desalination, right? Osmotic power harvesting, when a less concentrated solution and a highly concentrated solution, they're made to come in contact. And because of that, there's a current through an external circuit. So in all these applications, liquids come into contact with 2D materials. So it's important and interesting to understand what is the physics behind such interactions. Now, with that background, my talk will have mainly two parts. In the first part, I'll discuss the wetting and frictional properties of molybdenum disulfide. And in the second part, I'll discuss the wetting and boron nitride. So these are the two heteropolar two-dimensional materials that we'll be focusing on in this talk. Now, in terms of understanding the wetting properties of 2D materials, the main property to look at is the contact angle of, in principle, any liquid, but mainly water on the surface, right? So that's one easy way you can characterize the interface. And we all know that if the contact angle theta is greater than 90, then it's a hydrophobic surface. But if that is less than 90 degrees, then we have a hydrophilic surface. And molecular dynamic simulations can actually provide atomic level insight into how water molecules kind of orient at the interface, or how they arrange into layers at the surface. So this can be used for simulation assisted design and physical understanding. And it basically involves Newton's laws of motion applied to each atom and molecule, whereby you can predict the drop profile and other properties. Now, before we go ahead, I wanted to ask you a question. If you knew that molybdenum disulfide and graphite was a bit surprising to us, because graphite, as we know, is non-polar, but we thought that MOS2 should be a polar material, but it apparently not. So we'll try to explain why that is. Now, before we do any kind of molecular dynamic simulations, you need to obtain the force field parameters that go into it, because any simulation will be as good as the parameters that go into it. Now, in terms of parameters, you have bonded interactions within the material. For example, the molybdenum and sulfur atoms are connected by bonds and angles, modeled as harmonic potentials. So that's these half k L squared or half k theta squared terms. And the non-bonded interactions between, say, the material and water is modeled through a Leonard-Jones potential, where you have these dispersion attractive interactions. So that's the minus sign here. And you have a repulsion due to the nuclei repelling each other. You also have charge separation within the material, where molybdenum is positively charged and sulfur is negatively charged in an overall sense. So that's accounted through these partial charges here. Now, these partial charges, they come from quantum mechanical calculations, whereas the all the bond and angle constants, as well as the Leonard-Jones parameters, we obtained by carrying out a fitting to the lattice and elastic constants of the material. Now, these are the important parameters here, the lattice parameters and the elastic constants. And I'll show how they match with the predicted values on the next slide. So this is the unit cell of MOS2. So these are the three length-based lattice parameters, A, B, and C. And you also have three angles here, alpha, beta, and gamma. And the elastic constants are basically second-order derivatives of the system internal energy with respect to the strain in different directions. Now, we looked at all these properties. So these are the lattice constants. These are the elastic constants. We compared these properties between the experimental values and the fit from the force field, and we found that there is relatively good match between these. So this force field is able to predict the bulk properties of MOS2 very well. But what we did here was we split the intra-sheet and inter-sheet interactions. So we expect that this force field could do well in interfacial applications involving liquids as well. So we went ahead and tested the performance of the force field in interfacial applications by trying to simulate the contact angle. And we used three layers of the material to represent the bulk material, and the atoms of the material were initially kept frozen at their equilibrium positions. Later, we showed that it doesn't actually matter. Even if you vibrate the atoms, the contact angle does not change much. And just for details, I'm using shortcomings of the model, but this is a very simple model, so a lot of people use it. And geometric mean combining rules are used to get interactions between unlike atoms like molybdenum and oxygen or molybdenum and hydrogen. Now, this is a snapshot of an SPCE water model. You have negative charge on oxygen and a positive charge on hydrogen. And this is, for example, a movie of a molecular dynamics simulation, wherein you can see that you start with kind of a fake cubic droplet. And as time proceeds, this droplet kind of equilibrates in the surface, and you can extract the contact angle through the tangent drawn at the surface. Now, because these are nanoscale droplets, you need to account for the effect of line tension, and that is done. And finally, you can get the contact angle on the surface. So we used various force fields to try to get the contact angle. There were some force fields in the literature which predicted complete wetting of the surface as compared to the experimental value of 69 degrees for the contact angle. There are also other force fields which predicted higher and they were modeling the interaction weakly between the surfaces. Whereas our work, due to the inter and intra-molecular actions, we are able to predict a good match between the experiment and the so now that the force field is actually working well, we can think of asking how do the charges inside the material affect the interfacial properties. So there's a charge of minus 0.25 electrons effectively from quantum mechanics, and there's a charge of plus 0.5 on the molybdenum atoms. So how much do these charges affect the interfacial properties of MOS2? So to quantify that, we split the interaction energy between the surface and the liquid into electrostatic part and a dispersion part. And out of the total interaction energy, we saw that whether it's a non-polar liquid like diiodomethane or it's a polar liquid like water, or an ionic liquid, the percentage of the electrostatic energy contribution to the total interaction energy, it is always less than 1%, right? So that points to some universality in terms of all liquids interacting with the surface only with dispersion interactions. So this explains the non-polar behavior of MOS2 and how MOS2 and graphene are pretty similar for gas physisorption. Now, what is the universality behind this? To answer that, we decided to look at the electrostatic potential above the MOS2 surface. So the surface is neutral as a whole, and if you were to apply Gauss law, then you would say the electric field is zero outside, but the charges are at discrete locations rather than being smeared out. So we can do an exact summation using a Fourier series expansion and try to get the electrostatic potential as a function of position above the MOS2 sheet. And this involves summing over all the atoms in and we use some space by using this formula, we plotted the contours for the interaction energy of an oxygen atom with the MOS2 sheet on top of it. So these are the electrostatic energy contours, these are the energy contours. And what we saw, the dispersion energy is almost an order of magnitude higher than the electrostatic interaction energy. And not only that, the electrostatic energy can be both positive and negative. So in effect, it can cancel out, leading to the low electrostatic contribution to the interaction energy. Now, if you plot the water density, this is the dotted black line here, you see that most of the water molecules are at around 3 angstroms from this 3 angstroms from the surface. And at this location, the solid lines which depict the electrostatic energy, they're almost zero. And that's why in this contour, you see that electrostatic energy is almost an order of magnitude less than the dispersion energy. So the reason for water not interacting electrostatically with the surface is not steric, as was claimed earlier, but simply that the electric potential decays rapidly outside the solid, so outside the basal plane of this material. So this is not to say that other planes of this material are non-polar, because when you have a material, you can expose different facets of this material. So the plane we investigated was the basal plane, but there's also armchair and zigzag planes of the material. And indeed, if you look at the percent contribution of the electrostatic energy to the interaction energy between the liquid and the solid, although it's very low for the basal plane, it can be pretty high for the armchair and zigzag plane. And what is one way to intuitively rationalize this? You can think of computing the contact angle of a polar sheet of MOS2 with charges included, and you can think of a fictitious non-polar MOS2 where you turn off the partial charges. Now, this is one advantage of molecular dynamics, where you can kind of tune what potential you want and try to understand the physics behind it. And you see exactly what we expected. When you consider the basal plane, because the contribution of electrostatics is very low, you can see that the contact angle does not change much whether you have partial charges or you do not. But on the other hand, for the armchair and the zigzag planes, the contact angle actually goes down when you have partial charges, and it's higher when you do not have partial charges. So this is just to illustrate that electrostatics can still play an important role at the edges and in nanopores in molybdenum disulfide. We also looked at the friction coefficient, which is a non-equilibrium interfacial property, and this is basically related to slippage on the surface. You must have all known about the no-slip boundary condition, but at the nanoscale, there can be some amount of slip on the surface, right? And this is quantified by the slip length, which is the fictitious length inside the surface where the velocity goes to zero. So the slip length is related to the viscosity as eta divided by lambda, and this lambda is called the friction coefficient and is computed as the autocorrelation function of the force between the solid and the liquid. So we computed the friction coefficient and we saw that it doesn't change whether you have partial charges on MOS2 or you do not. And this is different than the comparison between HPN and graphene. On HPN, researchers had shown that the electrostatics can influence the friction coefficient a lot using ab initio simulations. And we found something which was totally contradicting that. And this is because of the way the MOS2 is structured. So MOS2 has this tri-layered sandwich structure, and because of that, the dispersion energy has undulations of the order of 50 millielectron volts, and that is high enough to cause difficulty to water to move on the surface. So that's why already the effect of the undulations in the potential energy landscape due to dispersion are high, such that when you turn on electrostatics, the undulations provided by it are not high enough to change the potential energy landscape. This is different on BN, right? Because this is a single layer, so the dispersion energy is fairly constant on the surface. So when you introduce electrostatics, you start to have a lot of undulations in the landscape, and that changes the friction coefficient by a lot. So that brings me to the conclusion of the first part of my talk. We developed a new force field for MOS2 by splitting inter and intra-material interactions. We then validated the force field using the interfacial behavior of MOS2. We showed that dispersion interactions dominate electrostatics in both determining the wetting and friction properties of the basal plane. However, we also showed that other planes in MOS2 are polar with respect to wetting. We found a slip length of about 10 angstroms on the basal plane. So this brings me to the end of the first part of my talk. I now want to go on to the second part, which deals with a slightly different case of HBN, which I already alluded to in the first part of the talk. And here we try to adopt a slightly more advanced approach to develop the force field. Uh, Again, we separated the intra and intersheet interactions. However, we used ab initio density functional theory to calculate the bonded parameters, because DFT is very good at predicting such parameters. The non-bonded parameters we obtained again by fitting to the mechanical properties. So this is what a force field looks like. You have bonds, angles, and improper dihedrals for the material. So the bond is between, say, boron and nitrogen. The angles are, you can have a BNB angle or an BNB angle or an NBN angle. And then you also have dihedrals, which quantify how much the atoms are moving out of the plane. So we carried out ab initio molecular dynamics, and then we fit these three parameters here. Then we went ahead and fit the non-bonded parameters to reproduce the crystal structure and the elastic constants. So all the quantities which are given in red, they're used in the fitting procedure, and the quantities given in black, they are merely predicted. So you can see that not only the fitted properties are predicted well, but also the properties which are not fitted, they're also within 10% of the 10 to 15% of the values that we see. We also looked at the phonon dispersion relation of HPN, which is another metric to see how well the force field is performing. And at least for the low energy phonons, which represents the vibrational material of properties of the material, the force field was able to perform well. For a note for the specialists here, that in MD simulations, you have these 1-4 interactions, and these were implemented differently for an HPN. We also scaled the 1-4 interactions by a factor of 0 rather than the typical 0.5 due to the strong Coulombic attraction between the 1-4 pairs here, the B and N pairs. Now, the improper dihedrals, although they do not affect the mechanical properties, but they are important for ab initio potential energy predictions using this force field. We saw that the force field predicts water layer interactions accurately. We took one water molecule and moved it away from the surface at a fixed XY position. And the dashed black line is the prediction from our force field. We also looked at other results from ab initio calculations. This DMC, or diffusion Monte Carlo, is a very accurate method to predict van der Waals interaction energies. And the other tools mentioned here, they are dispersion corrected density functional theory. Now, density functional theory, even when it is corrected for dispersion interactions, it actually overbinds for the van der Waals interactions. And this is what you see here, that all these DFT methods, if you use them to make a force field, they will actually predict complete wetting of water by the surface, whereas our force field matches the advanced ab initio calculation. So that's the take-home message from this slide. So with this accurate force field, we again simulated the HPN interface, but instead of just considering one liquid, we considered three different liquids here. We looked at ethylene glycol, which is sort of a polar liquid. So it's in between diiodomethane, which is a non-polar liquid, and water, which is highly polar. We use three different force fields for modeling these liquids because those are the most accurate force fields available to model those molecules at this time. And since we are looking at interfaces, the surface tension is a very important property. So we predicted the surface tension for all these three liquids. And in all these cases, we see a very good match with the experimental data. Now, to get the contact angles, we followed a slightly different procedure. Instead of looking at the tangent to the surface, we decided to use directly the work of adhesion because this is free from errors such as where the tangent is drawn, determining the contact angle. Now, the work of adhesion is the free energy change required to convert an HBN liquid interface to a vacuum liquid interface. And this work of adhesion can be calculated using a tool called free energy perturbation. And then this work of adhesion can be related to the surface tension and the contact angle through something known as the Young-Dupré equation. So through the Young-Dupré equation, we got the total work of adhesion and the polar component of the work of adhesion. Again, we saw that the polar component of the work of adhesion is very low, meaning that the wetting properties are liquid electrostatic interactions. And also, another point to note is that the simulations qualitatively predict the mild hydrophilicity of the HPN basal plane that is seen experimentally. Now, after having studied the equilibrium interactions, we also looked at the dynamic properties of the surface, which is again quantified by the friction coefficient. You've already seen this plot as to what the friction.
Anand, could we please wrap up in 2 minutes? We have 7 more minutes in the session. Thanks.
Yes, I will do that. Right. So we calculate the friction coefficient for these three liquids, and to our surprise, if you do not have electrostatics, it's water which has the lowest friction coefficient, followed by ethylene glycol and diadomethane. However, when you bring about electrostatic, the order actually flips and now becomes the liquid with the highest friction coefficient. This means that liquids which have a lower wettability, so water has a higher contact angle, it can still have a higher friction on the surface, and this is mainly due to electrostatic interactions. Another interesting point we saw is that the organic liquids have very high slip lengths. So if you take the experimental viscosities of these liquids and you compute the slip length, even with electrostatics included, the slip length of ethylene glycol or diadomethane is about like 50 times higher than the slip length of water. And this is something which should be experimentally investigated. And this might lead to the development of methods for separating water from organics simply based on their flow on nanoscale surfaces. One important thing you could check in your simulations is the orientation of the interfacial liquid molecules through contour plots, which depict how the angles of made by the water molecules are with the normal to the surface. And we saw that even when you include electrostatics, these orientational plots do not change. So what is merely changing is the force that acts by the solid on the liquid molecules. And we came up with a physically motivated metric to rationalize the changes in friction. Because the friction is this autocorrelation, you can think of it as the mean squared force multiplied by a time scale. And actually, this mean squared force goes up by a lot when you introduce electrostatics. So even though the friction coefficient goes up by only 3.9, the mean squared force actually goes up by 9.7 when you include electrostatics for the case of water. Now, why is the friction coefficient only increasing 3.9? It's because the decorrelation time falls when you introduce the electrostatic interactions. So we saw that as well. That you can extract the decorrelation time based on a simple kind of two decaying exponential functions, and you can fit that to get the decay time. And we find that the decay time actually goes down for water compared to ethylene glycol and diadomethane. And that is expected, right? If there's more force acting on the water molecules, they're going to forget their previous configurations more easily. And that's why the decorrelation time will fall down. So with that, I'd like to conclude my talk. I discussed here the development of an MD force field for HPN, And we showed that liquids with lower wettability can have higher friction on HPN due to electrostatics. We also found that organic liquids can have higher slip lengths than water due to electrostatics. And finally, we discussed the role of the decorrelation time in increasing the in reducing the friction coefficient as compared to the solid liquid force. So in summary, we looked at the wetting and frictional properties of both MS and HPN, and we looked at the different roles that electrostatics can play in both the wetting and frictional properties. Thank you very much for listening, and I'd like to take any questions.
Thank you, Anand, for the very nice talk. So now the floor is open for questions, for a couple of questions.
Sushmita, can I ask one?
Yes, please, Basa.
Hey, Anant, very nice talk. I have a question about, so you if I understand correctly, you mentioned that, you're really looking at the atomistic level and then trying to look at, the potentials and all that, right? Why not, the kind of a Debye-Huckel or, one of those approaches? Why would you go for atomic, level of, description?
Right.
Yeah.
Correct. Right. So we are not looking at Debye-Huckel here because there are no ions in the system, and the Debye-Huckel kind of theories, they are very good for ions dispersed in liquids because they are dilute systems. When it comes to water molecules, the concentration is very high, right? Like the molarity of water is 55 moles per liter. So at that kind of density, the correlations between the liquid molecules, they start to become very important. Now, there are some theories which you can use. They're called statistical theories for liquids. Maybe you will probably be knowing them. Like there's this Ornstein-Zernik equation, which can be used to get the correlation function. But these days, due to computational power, people are trying to use molecular dynamics because it's more convenient and amenable to get the information from those simulations.
Okay. Yeah. Thanks. Thank you.
Hi, Susmita.
Thank
I
you.
have one question.
Yeah, Dilip, go on.
Hi, it's nice talk. See, I have one question.
you.
What is the motivation behind studying the MOS2 surface? If it is the layered structure of MOS2, can we generalize those results to graphene, for example, which is another layered material?
Right. So the motivation to study all these 2D materials is mainly want to make desalination membranes out of them, or if you want to do osmotic power harvesting out of them. In all these cases, the liquids will come in contact with the MOS surfaces. In fact, there are attempts to use these materials as sensors because you can dissolve or you can suspend them in solutions, even in water, to use as surfactants. And they emit light. You can try to modulate the light when certain organic or molecules are absorbed, and thereby you can use them as sensors. That's the motivation for studying how electrostatics impacts the properties of interfaces with liquids. And yes, I mean, similar results have been, but graphene is much simpler because there are no electrostatic interactions. It is simply a non-polar material. There's no electrostatic.
Okay, thanks.
Okay, thanks. So if anyone else has any questions, please put them on the Q&A session, and Dr. Anand will take that up. So we conclude the second session of SMYIM. Now we'll move to the poster session. I'll hand it over to Basa for a quick introduction of the judges.
Hello. Hey, hi. Yeah, so welcome to the poster session. Just give me a second. So we have Udipta from IIT Gandhinagar, who spoke about compound droplets in the morning session, and Jason, who again just spoke a couple of one talk ago about drag reduction problem. Jason is a faculty at IIT Bombay. He did his PhD at IIT Madras with Professor Pushpavanam, and a postdoc at ICTS Bangalore. And he's been with I guess IIT Bombay for a year plus now. And Udipta is at the Department of Mechanical Engineering. Before that, he did his bachelor's, master's, and postdoc as well from IIT Kharagpur. Okay, with that introduction, I would like to welcome both Jason and Udipta for agreeing to evaluate the posters. And they're going to be there today as well as for tomorrow's poster session as well. And just to make an announcement that we are going to have 3 poster prizes, and these poster prizes are sponsored by RSC Soft Matter. They're going to be called Soft Matter poster prizes. So with that, we begin with, I welcome Jason and Udipta to take over.
So hello again, and thank you very much, Professor Basava, for this nice introduction. And I think we are already running little bit late. So what I'll do is I'll start with the poster presentations, and I'll go in the order in which which has been provided to us. So the first presenter is Mr. Vaibhav Raj Singh Parmar, who is from RRI, and the topic of his presentation is the title of his presentation is effect of aging on cracking of desiccating laponite suspensions. Yeah. So if the video can be played, I think we can start with that.
My topic is effect of aging on cracking of desiccating laponite suspension. This is a picture of mud cracks that is formed due to the desiccation of mud. There are 4 processes involved in forming this type of final pattern: desiccation, contraction, nucleation, and crack propagation. If we do this type of experiment in a lab, there are many factors that affect the crack pattern, such as material, solvent, substrate, thickness of the drying film, environmental condition, and also environmental conditions such as temperature and humidity is also affect the pattern. For our experiment, we use laponite, which is a nanometer size clay, which has a negative charge on its face and a positive charge on its rims. This laponite is an aging sample, and this aging can be controlled by adding salt or by increasing the laponite concentration in a sample. So as seen from this picture, gelation time strongly depends on the salt and laponite concentration. As the laponite concentration or the salt concentration is increasing, the gelation time decreases. So for our experiment, we made the desired laponite concentration suspension with desired salt concentration, and then we filtered it using 0.45 micron filter. Then we took the sample and placed it in a petri dish, and the petri dish is placed inside an oven in which the humidity is also controlled using salt solution. So the film thickness that we use is 0.7, and the petri dish diameter is 4.65 centimeter. Temperature is 50 centigrade. This is a picture of pattern that we got. So it contains the cracks and also the shrinkage area. We calculated also the crack area and also the shrinkage area separately. So let's see the effect of concentration, laponite concentration. So these pictures are about 2.88% concentration. This is about 3.5. If we see the normalized crack area, so they are not very different, but the crack area about the higher concentration is high. The shrinkage shrinkage is 7.3 and 7.7. Now, what if we add the salt in this system? So if we add salt of 2 millimolars of NaCl, then these 2 pictures are for 2.8 and these 2 pictures are for 3.58%. The first observation is that for the higher concentration of laponite at 2 millimolar, the cracks are no longer so straight. They are showing wavy behavior. The other thing is that if we see the crack area is higher for 3.58%. But if for the salt, if we compare the shrinkage with the aqueous suspension, the shrinkage is very less for the salt solution. The third observation is if this is the final pattern, it has two edges. One is formed due to shrinkage and one due to formed due to crack formation. So the one that has formed due to shrinkage are less sharp, and then the one that has formed due to crack is more sharp, which means that there is a fluid-like behavior at the time of shrinking. So, so the conclusion is the difference between cracks for aqueous suspension and salt solution is visible at a high concentration of leponite. Crack area increases and increasing in aqueous leponite suspension. And if we add salt, then the shrinking will be reduced. Baby cracks are observed if the aging is fast, which means for high salt concentration. And also, if aging is fast, then only sharp boundaries are observed. I would like to thank my ma'am, Professor Anjali Bandyopadhyay, and all lab members for their discussion.
Okay, thank you very much. So then I'll open the floor for questioning. If you have any questions, you can ask. I guess the speaker is here, Vaibhav.
Yes.
Are you present? Yeah. So I will open the panel for questioning. So if you have any questions, you can ask Vaibhav.
Vaibhav, I have a question.
Yes.
Hey, so what is the reason for choosing? See, typically these desiccation experiments or the crack experiment that you're doing, they're done by sessile drop, drying, and things like that, right? What is the motivation for you to choose this particular drying configuration?
So the drying, the concentration we use for these experiment is used because the laponite is studied in these concentration is well known, and I can find literature, and I can find the physical properties corresponding to these concentrations, so that I can correlate them with my results. And also, so the other part is that the laponite has different phases or at different concentration. So I chose the 2.8 and 3.5 concentration because at after some aging time it will form glass at these concentrations.
The question was about the drying configuration. You know, you have taken a petri dish and you have taken a dispersion and dried, right? I mean, why would you choose that?
So you mean the application of this?
Not the application. See, if I look at the experimental geometry that you consider, right? Okay. You have taken a petri dish, right? Mm-hmm. It's a petri dish in which you have taken a clay suspension. You are drying it.
Yes, ma'am.
Right.
So okay, so yeah, I understood. So if I'm not taking a petri dish, but I only observe a drop that is drying, so the process that that are involved there is different because it has a contact. It has a contact angle in the process. So there, if I don't use a petri dish and only use only a drop, then there will be some coffee ring effect type. But now I am studying the patterns that are formed due to desiccation. So these no, yes.
Yeah. Okay. Sounds good. Yeah. Thank you. Thank you.
Okay. So if anybody else has further questions, please go ahead and ask. Still have some time.
Hi, I have a question. Danny here.
Yes.
Hi, Vaibhav. So I have a question regarding your cracks. It looks like when two cracks meet, the angle is close to 90. Is that right?
Yes.
So what is the reason there?
So the cracks will always travel where they can relax the maximum amount of stress in the sample. So stress is only relaxed if there is one crack in the sample. So it means that the stresses that are perpendicular to that crack are relaxed. So if a crack is traveling near the crack that is already formed, it will meet at 90 degrees.
Okay, I think I lost you there for a few seconds.
Yeah, me too. I think there was a connection problem.
Oh, maybe a
Yes, so
driver
I
question.
can
If you don't mind, can you just repeat what you just said the last few seconds? Maybe?
Yes, so I was saying that so if the cracks meet at 90 degree is because the system wants the maximum release of stress on from the energy argument, the maximum elastic energy will be more if the cracks meet at 90 degree. Because the cracks that is formed already release the stress that is perpendicular to that crack.
Oh,
And the
okay.
maximum stress at that point will be only parallel to the crack that is already formed. So the new crack will only meet the already made crack at 90 degrees.
Okay, and just a quick follow-up question. So why does a few cracks don't travel in straight lines? And yeah, thanks for that. So the ones that travel along the boundary in some sense.
Yes.
I mean, why is that? What's the mechanism there? Can you tell?
So these we observed for only high concentration of leponite and when there is a presence of salt. So the exact reason we don't know, but I think that at the point of drying, since solvent is evaporating, the salt concentration in the sample is increasing with time. So if the salt concentration is increasing with time, so the system will become stable at some point and unstable at other points where the salt concentration is more. So maybe that's why, but we need to do more experiments to understand it clearly.
Okay, thanks.
I have one question.
Yes, sir.
Hi, can you explain the increase in crack length with salt concentration? I didn't get your point. Why the crack length increases?
So the crack area increases. Yes.
Area increases, yeah. What is the reason for that?
Yes. So since laponite is an aging sample, so if we increase the laponite concentration, so the crack area should increase because it will show the solid like behavior earlier. So if the solid like behavior is present in the sample earlier, so due to in the process of desiccation, the cracks are all formed due to the stress that is implied that the substrate will give to the sample, and if the sample is solid first, so the cracks will made earlier, and then the crack area will be increased because it will originate earlier in time.
Okay. But are you changing the salt concentration or not?
Yeah, I changed the salt concentration also and the laponite concentration also, but both in the rheological experiment both shows the same effect, that the aging crossover will be shifted to the lower wetting time, which means it will show the solid behavior first.
Okay, I think that's all the time we have for this particular presentation. If there are further questions, you can raise the questions in the chat, and I guess Vaibhav can answer them. By typing the answer. So we'll move on to the next presentation. Next up is Sanjay Khawas, who is from IIT Bombay, and he will be talking about evaporative self-assembly of gold nanorods. So.
Have we studied the assembly of gold nanorods? And how does this assembly can be in particle concentration? At first, we synthesize the gold nanorods following the heat-mediated growth process. And the synthesized gold nanorods have a positive charge and have a theta potential approximately 44.5 millivolt. So we need 5 different samples of different concentration. First, we take the microliter of suspension and cast it on a silicon substrate and allow it to dry at room temperature and humidity. After complete evaporation, we found a protein-like structure is formed on the silicon substrate. During drying, we found a distinct mode of evaporation, the advancing mode, constant contact angle mode, and constant contact radius mode. During constant contact radius mode, the three-phase contact line of droplet get into the silicon substrate, and the particles are dragged towards the drop edge by the outward flow. And then these particles are accumulated near the three-phase contact line, and after complete erosion, they form an inline structure. The microscopic images of ring of this final deposition reveal that it contains four distinct regions: the outer region, the curving region, the depression region, and the central region. And these are the magnified images of the outer region and the curving region. So with the extra particle concentration, we found that the range becomes wider, because with the increase of the particle concentration, a large number of particles or more number of particles are get accumulating at the surface contact line. It is also found that with the increase of the particle concentration, the assembly structures are getting more order, as with the increase of the particle concentration, viscous property of solvent molecule increases, which so there will be less possibility for the assembly structure to be disturbed by the fluid flow. And we also found that the particles are arranged in a symmetric manner. That is because of the fluid, it is due to the competition between impulse electrostatic and attractive and lower interaction. So, in conclusion, we can say that we were able to achieve a self-assembly, a long-range order self-assembly structure by aerobatic self-assembly technique, and this self-assembly structure can be tuned by tuning the particle concentration. And we know that the final erosion pattern largely depends on the fluid dynamics. So, change in surface tension also causes change in fluid dynamics, so resulting in a change in final erosion pattern. So, the introduction of surfactant molecules into suspension would be a great approach for the future. Thank you.
Okay, so the floor is now open for questioning. If you have any questions, you can ask Sanjay. I think Sanjay is here. Sanjay, can you respond?
Yes.
Yeah, sure. Yeah, sure. Go ahead.
Hey, Sanjay. So I noticed that in your results, when you are presenting the effect of concentration of the particles, you used nanomolar as the units for the concentration of gold nanorods. But typically in colloids literature, you would see that people use weight fraction or volume fraction. So any reason why you have chosen such a representation in your case?
This is actually, sir, weight by weight concentration. We represented nanomolar concentration. That's nothing particular. There is nothing particular reason, but just we use.
Okay, no worries. Yeah, thanks.
Okay, so if there are any further questions, please go ahead and ask.
Hi, Sanjay.
Yes, sir.
This is Dilip here. I also observed in that same result section, you have a very nice ordering at certain concentration.
Yes, sir.
How do you explain that? Why the ordering happens for that particular concentration? I think this D figure D here.
Basically, what we initially think that during the constant contact and constant contact radius mode, at first the particles arrange themselves side by side. So they form a long-range chain-like structure, and these chains then stack layer by layer. So when the fluid with the increase of the particle concentration, the viscous property of the suspension actually getting increased. So it resists the fluid motion actually. So for the higher concentrated sample, there will be less possibility that the self-assembly structure to be disturbed by this fluid motion. That's how I actually discussed this result. So this is in respect with the respect of the viscous property of the suspension.
All right. So how monodisperse these rods are? These gold nanorods are? What is the size polydispersity? Have you measured that?
Polydispersity actually we measure zeta potential, but the monodisperse or polydisperse we didn't measure actually. We take the average actually. We actually take some 10 images and then took the average. Actually, we measure the length and measure the length of some nanorods and as well as the diameter, and then the average out, and that's how we measure the size of this.
Thanks a lot.
Thanks. If there are, I guess we have time for maybe one more question. If there is any other question, please go ahead.
Sanjay, this is Jason. I have a question. So, do you expect there to be any difference in the kind of patterns you see if you had spherical particles instead of rods? Or does the rod nature have any role to play in your observations?
Yes, sir. Basically, for isotopic particles, there is no particular direction actually. So they also form the order structure, but here, in this case, we have for this anisotropic particles like nanorods. They have certain direction of this particle. Like here, they actually for the inner side of the ring, they are oriented along the radial direction actually. So for isotopic particles, there will be no change in the pattern, but for the application point of view, if we see this nanorods assembly would be more actually helpful. Actually, in the pattern, there will be no change. I think so.
Hi, Jason. This is Sunita. I am the second author of the poster. If I'm allowed to maybe throw some more insight into what Sanjay is saying.
Yeah, sure. Go ahead. But can you be very quick because we are running out of time? So, if you could briefly.
For the spherical particle, we have just published one paper. It depends on the surface coating. Okay, so if the C-type is the surface coating, generally what we see is just a formation of a coffee ring only. The paper that I'm talking about, we have done an elaborate work on it. We have changed the surface functionalization, and there we see some very interesting, this concentric ring-like pattern that has been published in Advanced Matter interfaces recently. So if you want to discuss more, I am here till the end of the session. We can talk about it.
Yeah. So thank you, and I think if there are further questions, you can type the questions in the chat, and I believe those can be answered. Or you can also privately contact the speakers and the authors of this work. So next, we'll move on to the next presentation. Next up is Vegesina Sarath Chandra Verma, who is from IISc Bangalore, and the topic of the presentation is universality in coalescence of polymeric fluids. So the video can be started.
I work on coalescence of polymeric fluids. Coalescence proceeds by a formation of nuclearies, as you can see here in figure 1. In literature, for neutronium fluids, specified universal behavior is proposed by Paulson et al. By the balance of surface tension, inertial, and viscous force. In viscous regime, various scales have time, and in inertial regime, various scales have time force modifiers. Coming to polymeric fluids, as there exist chain entanglement and molecular interaction, leading to an initial complexity. So the question is whether a universality exists in coalescence of polymeric liquids. To answer this, we have performed experiments on 4 different water-soluble polymers, namely PAN, PEA, PEG, and PEGA, with different concentrations which span over dilute to semi-dilute entanglement. All the fluid characterization was done using NCR 302 rheometer with cone and plate 40 mm and 1 degree angle geometry. As a representation, the flow curves of PEO and PEA are shown here for concentrations 0.2% to 0.6%, where PEO is showing typical shear filling behavior and PEA is showing constant viscosity behavior in this particular strain rate. Fluorescence is achieved by dispensing a 2 mm droplet initially on a substrate and bringing a pendant drop towards a crystal drop with an approach velocity of 10 to the -4 meters per second. All the experiments were recorded using a high-speed camera at 90,000 fps and image analysis was performed in MATLAB. The characteristic length scales RC and time scales TC are obtained by balancing elastic, inertial, and surface tension forces, leading to RC is equal to root of U naught lambda, TC is equal to on-side number into lambda, where lambda is relaxation time of the fluid and U naught is kinematic viscosity of the fluid. Non-dimensionalizing length radius R and time T using characteristic time scales and length scales led to a universal scaling as shown here, which is R star proportional to C star power 0.2. Where C by C star is added empirically in non-dimensional time. To verify our scaling law, we employed linear PTT models and assuming flow as quasi-steady and quasi-radial, and by implementing the following scalings and approximations into moment and inflation led to a final differential equation of this form. The numerical solution of the differential equation gave the scaling of R star proportional to C star power 0.34, which is shown here, which is in good agreement with experimental results. So finally, we propose a new scaling law for coalescence of polymeric liquids, which is validated using a linear PTT model.
Okay. Thank you very much for the video. So the floor is now open for questioning. If you have any questions, I believe Sarit is here.
Yes, sir.
Yeah, so if there are any questions, please go ahead and ask. So once again, if you have any questions, please go ahead and ask.
Yeah, this is Jason. Thanks for the nice poster presentation. One question is, maybe I didn't catch it. Did you see the crossover from viscous to inertial in your polymeric fluids?
No, we didn't see any crossover. As of for Newtonian fluids, it is around 10 power -6 seconds. So our frame rate was not able to capture that.
I see. So you were only in the inertial regime.
Inertial regime.
Yes. I see. And secondly, in the model, I mean, your equation you wrote at the end, that is based on lubrication theory?
No, it is not on based of lubrication theory. Just a linear PTT model employing following scalings which I have provided on basis of Wiesenberg number reduced to the differential equation. It was not lubrication approximation.
Okay, and finally, how does the Wiesenberg number come in physically in this problem? Like,
actually, because of polymers, there is an elastic force. So, as there is an elastic force which is governing the balance between elastic and inertial forces, I have used Wiesenberg number. Basically, Wiesenberg number is introduced on basis of elasticity.
Sarat, I have a question. Udipta, can I ask a question?
Yeah, please go ahead.
See, I see that you've used PEO and PVA, some of these polymers, right? Is it possible that some of these polymers are surface active, and is there a, would you also consider the surface activity of these polymers as well in your analysis, and how is that taken care as of now?
I didn't consider any surface activities.
Because PEO is known to be surface active, right? If you take a even a drop or of PEO. PEO is known to adsorb to the interface, and it changes the interface properties. So in that context, is there any role of such interfacially active species, and has that been considered in your analysis?
No, as the work is focused mainly on the neck region, we didn't consider anything about the substrate properties or how substrate and polymer is interacting.
Yeah, thanks.
Okay, so maybe we have time for one more question. Okay, maybe I'll ask the question. So, Sarath, in the differential equation that you showed for the radius, I guess, for r, so it is. So if you come down a little bit, I guess. So the final equation that you are solving, I saw that. So in this equation, you have a dr dt square term, and also you have a dr dt term. So I'm wondering how many roots does this equation have? And which root are you selecting? How are you deciding the root that you're selecting?
So essentially we have 4 roots. It is leading to a 4th order equation, and one is 2 of them are complex. One equation which is a real solution, I have used both real solutions are almost giving the same result.
So both the solutions are giving the same result. Okay.
Almost, yeah.
Almost. That means they are different in some. What way are they different?
Exponent is changing within the order of plus or minus 0.2. 0.2.
So how do you choose one particular solution over the other?
We chose a solution which was giving us the approximate result towards experimental data.
All right. Thank you, Sarath. So we'll have to end the session here, and then we'll move on to the next speaker. Next up is Sriram Krishnamurthy, who is from IIT Madras, and Sriram will be talking about kinetic model for the aggregation of A beta 40 peptide under different shear conditions. So the video may be started.
Hi, I'm Sriram Krishnamurthy from IIT Madras. I'm working with Dr. Day1. Today I'm going to present on the topic modeling of the kinetics of aggregation of amyloid beta under different shear conditions. So we all, it's particularly known that amyloid proteins aggregate in fibril forms. This can lead to several diseases like diabetes, Alzheimer's, and Parkinson's, etc. So these proteins are very sensitive to external environments like pH, temperature, shear, etc. So in this work, we are going to look at the kinetic modeling of amyloid beta under shear. So it is generally known that shear actually accelerates the formation of aggregates. In this case, we see that when the shear environments are different, there is starkly different behavior of proteins. The kinetic behavior of the proteins is very different under different shear environments. So we have done 2 different types of experiments. One is a steady shear experiment with the co-ed cell. The other one is an unsteady shear experiment with the microplate well. So in the steady shear experiments, the amyloid solution is subjected to a steady shear in the co-ed cell. In the unsteady shear experiment, the microplate well is agitated at different speeds to get different levels of agitation, different magnitudes of agitation. So we have used a population balance model, which has 4 different steps: the nucleation step, elongation step, fragmentation step, and the depolymerization step. Each of these steps is associated with a rate constant, the Kn, Ke, Kt, and Kf. So this is the equation that governs. This is the population balance equation that governs the kinetics of fibril formation. So these are the results for steady and unsteady shear experiments. In the first case, we can see that there is an acceleration in the fibril formation, as is evident from the slope of the graph. It is also interesting to see that there are different final equilibrium concentration of fibrils that are achieved in the steady shear case. With increasing shear rate, we see that the fibril concentration also increases. The second case, the behavior is very different. We can see that all the fibrils reach an equilibrium, final equilibrium state, which is very similar. But we can see that the lag time is sufficiently different for each case. So as the agitation speed is increased, the lag time decreases, so, which is very different from the behavior of the steady shear experiments. So this is a universal model which we have fitted with a single parameter. For the shear case, we have used the depolymerization rate constant as a fitting parameter, and we can see that the depolymerization rate decreases with increasing shear rate. And for the unsteady shear case, we observe that increasing the nucleation rate constant is sufficient enough to fit the data for different agitation speeds. So in this plot, we can clearly see that the accelerating effect of shear on fibril formation. So here we have plotted the rate of change of fibril formation with respect to shear. We can see that the blue and final violet curve give us that the maxima and fibril formation, rate of fibril formation is higher for higher shear rate. Similar graph is seen for unsteady shear rate. A particularly interesting thing to note is almost all the highest maxima and rate of change of fibril is happening under a window of normalized time. So in this case, we have used normalized time because each experiment in the different agitation rate is for different time interval. Therefore, a normalized time is being used in this case. In this slide, you can see that there are two different graphs that actually give us prediction of average fibril length. The first graph is for average fibril length of steady shear experiment. So in this case, we can see that the maxima in average length is higher for higher shear rate. And for the next graph, we can see that there's a plateau at a higher shear rate values. For each case, we can see that for every case, we can see that there's a plateau in average fibril length, which is higher for lower shear rate values. So this is very interesting behavior that the model has predicted for us. But in both the cases, we can see that the values asymptotically reach an equilibrium value of around 250 monomers per fiber. So the conclusion from our modeling and experiment is that the behavior of amyloid beta 40 under different shear environments is very different. They have different kinetic behavior, and further probe is needed to see whether some morphological differences there. And we also see that the simulated results are very well in agreement with the experiments. Thank you.
Okay, so I guess the video went on for a bit too long. It is supposed to be for about 3 minutes. Anyway, the floor is open for questioning. So I believe the speaker is available. Sriram is available, right?
Yes, sir. Am I audible?
Yeah. Yes, you are audible. So the floor is open for questioning. Please go ahead. So once again, the floor is open for questioning. Please go ahead if you have any questions.
I think Sriram asked questions for everybody, so I thought there would be many people asking questions. But hey, in your experimental data, I know your work, So
yeah.
In your experimental data, so see the plateau, right? I mean, so if you look at this is the first plot on the left. I can't see the. This is concentration.
Concentration versus time, is it?
Right now, that concentration versus time. What is this? Is the concentration of the fibrils, or?
Sir, it's a concentration of the fibrils measured using fluorescence
Okay.
THT fluorescence.
But has it been also verified by other means? I mean, is the fluorescence is the only approach, or is there, how do you confirm it?
So the experiments were done by Swati, and she has already done a few experiments before with nanoparticles and other systems, and she has established a kind of a calibration curve where she has a different concentration of fibrils with THT fluorescence. So we use that calibration curve to establish our data.
This fibril, I mean, does this the calibration that you use, does it depend only on the concentration of the fibrils as well as the are there other parameters of the fibrils? For example, would it depend on the distribution of the length of these fibrils? You know, some of those parameters as well, or is it only the concentration?
No, sir, it depends only on the amount of fibrils. So this THT is a dye which specifically binds to the beta sheet of the fibrils, and the more the number of beta sheets, the more fluorescence that you get. So it is directly proportional only to the amount of beta sheets and indirectly the amount of fibrils.
Thanks, Sriram.
Yes, sir.
Yeah, so if I can ask one question since others are not asking. So I keep seeing Sriram every day here. Sriram, so this kinetic population balance model, so there is no temperature in this model framework?
No, sir. All these experiments are conducted at same temperature, that is at physiological temperature of 37 degrees. So we have not actually considered, for example, are you asking about the effect of temperature on the rate constants, right?
Yeah, so that's what I was thinking.
So since all of these experiments are at the same temperature, we have not considered that.
I see. And I mean, so what I was expecting is that those rate constants should have a temperature dependent.
Yeah, sir. So there are papers that have talked about the effect of temperature on fibril formation and the effect of temperature on the kinetic parameters. But here our experiments don't require different temperatures.
Correct.
So our model also reflects that.
Okay. Yeah. Okay. Thanks.
Thank you, sir.
Okay, thank you. That's about the time that we have. So we will move on to the next speaker. Next is Mr. Anuj Chabra, who is from IIT Bombay. And Anuj will be talking about electrostatic interactions of the polyelectrolyte polymers attached to the spherical surface. So the video can be started.
Anuj Chabra, and I am here to talk about the electrostatic interactions in the polyelectrolyte brush on the spherical surface. So the motivation of this work is to understand how the DNA chains will interact with the counter ion when these are attached on the spherical surface. In one of this work, they try to simulate this for bulk DNAs, and they introduce NaCl and MgCl2 ions of different different concentration, and they found that even at a very low salt concentration, the MgCl2 ions, Mg2 plus ions can stabilize this DNA structure and can induce attraction between them. But whereas for NaCl, this was not the case. Even at a very high salt concentration, it was not happening. So our motivation of this work is to understand how this curvature will affect the DNA chains along with the counter ions if the NaCl2 and MgCl2 are added to the system. So this is our experimental data. So to understand this, we try to form BCC crystals, DNA gold nanoparticle superlattice, and we form three systems. In system A, DNA monomers at 13 base pairs, whereas system B has 50 and system C has 65. Out of 15 can form the Watson cake base pairing, leading to the formation of a BCC crystals. So we did the small angle X-ray scattering analysis, and from this we found that there is a peak shift. So you can see that these peaks are shifting with the increase of the salt concentration. This can indicate that there is some decrease in the superlattice size because of the introduction of the salt. So, but we calculated the brush length, that is this length from nanoparticle surface to the point where this brush ends, which we call edge, and we try to understand how this power law will follow. We see that for alpha values for MgCl2 is coming out to be almost twice to that of the NaCl, since it is an ionic strength. So indicating that there's some additional effect which is coming out in the play. We also did the fit the Dow-Cotton model given by this equation, where H is the brush length, R is the particle size, and N is the number of monomers, and K is the constant, and I is the ionic strength, and sigma is the charge density of this chain, of the number of chains. So this data fits perfectly with our experimental data, indicating that there is some additional effects which come up in the play in case of MgCl2. So what is this additional effect which is leading to the faster decrease in the DNA chains? This is called the ion bridging. In one of the work by Bosco et al., they tried to understand this, and they did a simulation work. And from this, they found that there is some ion bridging. That is, this divalent ion can break between the two phosphate backbones, leading to a faster decrease in the chain and a compact structure. So this is what is happening in our case. That for NaCl, their charge scaling is the dominating factor, and there is no ion bridging. But in case of NaCl2, both ion bridging as well as the charge scaling both comes into play. So which leads to a faster decrease and the compact structure. So thank you everyone for your attention.
Thanks for the nice video. I think it was right on time. So the floor is now open for questioning. The speaker is available, I believe, and you may go ahead and ask questions. So once again, I'll repeat that the floor is open for questioning, and you may go ahead and ask questions if you have any.
Udipta, can you scroll down the apps, the poster?
I believe Professor Dash can, yeah.
Yeah, hi. Can I follow up with a question?
Yes, sure.
So I see that you've listed the scattering as one of the tools that you're going to look at.
Yes, sir.
Can you just explain a little bit about what is there's a data there, right? SFQ versus wave.
Yes, sir. So can anybody slide to the top of the poster?
I think Sushmita, you should. He wants you to scroll up, or sorry, scroll down or whatever. So he wants to, yeah.
So here you can see an equation. IQ is equal to NF square PQ and SQ. So what we do is we get a form factor and a structure factor. The form factor is basically because of the when our system is very dilute. So what happens is when the system is dilute, there will be an intercorrelation between the nanoparticles. So we will get a form factor. So this SQ will be 1 at that point. We do a scattering for that, and then we make a BCC crystals. So using Watson-Crick base pairing, and those will give the this kind of equation which has both the form factor and the structure factor. Then we divide that equation to get the structure factor, which is given by this equation. So these structure factor will give some distinct peaks. So these peaks are in the ratio of 1:2/3, which gives a BCC crystal. So when we are increasing the salt concentration, this BCC crystal is decreasing, leading to a shift in the peaks, indicating that there is some decrease in the size, because this Q peak will be related to interplanar distance as D is equal to 2π/Q.
Yeah. So when you're interested to really look at the interaction between the spherical surface and the polyelectrolyte, right? That's what your objective is, right?
Yes, sir.
So then why would you go for a concentrated system? Isn't it possible to do an experiment at dilute concentrations and then get some information?
Sir, if we do the small angle scattering for a particle system with the DNA attached on it, since the gold nanoparticle has a very high scattering density, so the DNA and water has approximately the same scattering density, so there will be not much of a data we can interpret from that. So it will be approximately the same as that of a nanoparticle. If I have not shown that, so it will be this structure factor will be, sorry, this scattering will be the same as for that, almost the same for the nanoparticle and the particle which has the DNA attached on it. So we have to find an alternative way, which is this one, which we can find.
Okay, thank you. Thanks.
Okay, thank you. So any further questions, please go ahead. We still have maybe time for 1 or 2 more questions.
Well, if nobody is asking, I can ask one question. Hey, Anuja, it's a good work. So in all your measurements, you have a fixed density of fixed grafting density, right? Or
yes, sir.
I see. So will that also impact on the agglomeration which you are seeing here? Or?
So we did a further experiment. So there was some indication that there is some difference in that. So if we increase the particle size and do the same process, the particle officially there will be some decrease in the density of this particle. So since the particle density is decreasing, the polymer chains will have more space to move, and so they will more so they can form a smaller structure, which we were observed with the decrease in the grafting density, because these chains can move a little more in a variation compared to in an extended state. When these particles are smaller, what will happen is that there will be less space, so these chains will be more in an extended format.
I see. Okay, yeah. Okay, thank you. Yeah.
Thank you, sir.
Okay, I believe we are almost out of time, so we'll have to move on now. Our next speaker is Merin Jose, who is from IIT Madras, and Merin will be talking about evaporative self-assembly of binary mixture of soft colloids. That is, pardon me. So the video can be started.
I'm Merin Jose, a PhD student in IIT Madras. I'm going to present my poster on evaporative self-assembly of binary mixture of soft colloids. Self-assembly of colloidal particles at interfaces is a widely exploited research area. The addition of a small number of particles with different size has shown to suppress the long-range ordering in hard colloidal crystals. Here we see how the addition of different size particles manifests in the self-assembly when soft colloids replace hard colloids. We use here water-swollen microgel particles with a characteristic core shell structure. The core of the particles is highly cross-linked compared to the soft and deformable shell. These particles are also inherently surface active. Further, they have an exceptional property that while at the interface, they undergo deformation, attaining overall interfacial diameters larger than when they are in bulk. The extent of deformation depends on the internal structure of the microgels and also on the concentration of the microgel at the interface. The AFM topography images of the deposited microgels on substrate show the particle cores only and empty regions in between the cores. Whereas the phase contrast images show that the regions between the particle cores are not empty, instead occupied by the shells of the particles in close contact. We use the sessile drop evaporation to create self-assembled structures using colloidal particles. While the drop is drying, if you look at it under an optical microscope, you will see the hexagonal arrangement of particles. When the drop evaporates completely, we see a uniform monolayer deposit spanning the entire circular area. It should be noted here that the careful tuning of the concentration of particles in the drop is necessary to obtain the uniform monolayer. We refer to this concentration as the monolayer concentration. Next, we synthesized particles with two different diameters. The difference in the particle diameters when fully swollen in bulk is about 25%. The core plus shell sizes of the particles at monolayer concentration and below monolayer concentration show that the smaller particles shrink in size by about 20% and larger particles by 30% to maintain the hexagonal lattice at the monolayer concentration, where both the particles have roughly the same core plus shell sizes. Finally, we look at the binary monolayer deposit. Clearly, there is no segregation of particles based on size. Thus, we can conclude that while the lattice gets distorted to accommodate particles with different sizes for hard colloids, in soft colloids, the particles deform to preserve the lattice structure in the presence of different size particles. Thank you.
All right, that was very nicely timed. Exactly 2 minutes and 56 seconds. So I believe Marin is available. So the floor is now open for questioning. Please go ahead and ask questions if you have any. So once again, the floor is open for questioning. Please go ahead and ask questions.
Okay, I think students are not asking questions. Maybe, there are conferences like if a student asks, they get some free drinks or some cookies, something like that should be here also. So
yeah, it's difficult.
So nice talk. So I can ask one question. So when you are doing these evaporations, how about the polydispersity, or you get a accurate arrangement without any disorder in the sample?
Yeah. So if you look at the final deposit, you see that compared to the hard colloidal case, where when you induce particle with a different size, it leads to the long range distortion of the particle lattice. In the case of soft colloids, the particle with different size, the so-called foreign particle that comes into the lattice of the host lattice, it fits in nicely into the lattice and it behaves as though it is one among the particle of the host lattice. So thereby we can in fact see hexagons in which among the 6 vertices of the hexagons, you can see combination of the small large particle. So which means the lattice now does not distinguish between a small or a large particle, and the lattice stays hexagonal even when we mix particles with 2 different sizes. So this it is able to do this. The lattice is able to do because the particles are doing the adjustment, that they are deforming and able to maintain the lattice structure.
Okay. Thanks. It's a good work. Yeah.
Udipta, there is a talk by one of the attendees. There's a question. There's a question by one of the attendees.
Oh yeah, sure. Go ahead. Please go ahead.
Yeah. What is the concentration you have used in these experiments?
Yeah, so the concentration is the crucial thing. So we have to find the particular concentration at which, when we place a drop of the sample, of the microgel sample, these microgels are basically dispersed in water. So we find that particular concentration by performing series of trial experiments. We obtain that concentration at which the whole of the drop interface gets covered by the particles. So that concentration, we determine it separately for sample 1, which is let's say of diameter D1, and sample 2 of diameter D2. So the concentration, if we calculate when we find the concentration in weight percent, it comes about very small values like 0.02, 0.03 weight percent.
So you are able to track the concentration during the evaporation, right?
We are not tracking the concentration during evaporation. So what we do is, so let's say when we synthesize the particles and we have the concentrated solution, the mother solution we call it. So we dilute the mother solution several times and we place, we take drops and we look at the final deposit in each case. So we find that concentration at which we get the monolayer, like where we get the monolayer that covers the entire circular base area of the drop. So that concentration is our standard concentration. So based on that, we are doing the further experiments.
Okay. So is there any effect of this curvature?
That is, if we have particles enough to cover the whole of the interfacial area, so then it is basically forming a jammed interface. So now you cannot have, even if the particles are not being, they sort of form a very gel-like interface. So in that case, what the particles can do is they just descend. The monolayer just descends upon the loss of liquid from the drop, and it just descends, and at the final stage, it just gets transferred to the substrate, covering the entire circular area.
Okay, thank you.
I have a question. Do we have time for a question?
Yeah, maybe we have time for maybe one or two more questions here.
Okay.
Please go ahead.
Yeah, thanks. Thanks for the nice poster, Marin. So I have a quick question. So if I understood you right, when you have soft particles, they're able to deform and sit in the lattice properly.
Yes, correct.
Yeah. So I was wondering, in your experiments, is it possible to control the softness and maybe slowly make it harder and see a phase transition of some sort? Is that possible?
That's a very interesting question. So these particles, when we say they are soft microgel particles, the important characteristic of soft colloids is that their softness is tunable, and we have a control over the softness. So for that, what we do is, while doing the synthesis of these particles, we control the cross-linker amount. So if you add more of the cross-linker, what will happen is you get the colloids which are more hard. And if you add less cross-linker, you get colloids which are less hard or more soft. So we can in fact tune the softness of these microgel particles, and thereby we can control factors such as how much they deform at the interface and things like that. So it is possible.
Oh, okay. Very interesting. Thanks.
Okay. There is maybe time for one more question.
I want to ask one question.
Yes, please go ahead, Vaibhav.
Yeah, so since these particles, the size of these particles depend on temperature. So if the drying happens at one temperature and at another temperature, will there be any difference at the final button?
Yes. So yes, as you have correctly said, these particles are also thermoresponsive. In addition to they are soft and also thermoresponsive. So all our experiments are conducted at temperatures in room temperature in which the transition does not happen. So the transition temperature of these particles is around 32 degrees Celsius. So at that temperature, the particle undergoes sudden shrinking, sudden change in the particle size. So all our experiments are conducted at room temperature roughly around 25-26 degrees Celsius.
Thank you.
I have a question. Can I ask?
Yeah, maybe very quickly.
Okay, so very nice presentation, Marian. So I have a question regarding the concentration, the first part that you discussed. How do you experimentally characterize whether you have a monolayer at the air-water interface or multi-layer? What is the morphology there?
Yes. So basically, if you have, if you say that you have a monolayer that covers, or the particle concentration is just enough to cover the whole of the interfacial area, and you look at the deposit, we can image it by different techniques, SEM or AFM. So when you see a uniform monolayer that spans the entire area, you can say you have achieved the monolayer concentration. And if you go below that concentration, you will have a gap in the center, or some, you might see a monolayer coffee ring also. And if you go higher concentration, you will see multi-layer thick rings. So I think it's done by series of trial experiments. So when you are able to,
So when you make the
so I'm sorry, I have to cut in here. So if there are further questions, maybe can be asked in the chat or through private communication. So we'll have to move on because we are running out of time. We'll have to move to the next speaker. Again, extremely sorry for for ending the poster presentation. So the next speaker is Naveen Kumar Chandra, who is from ISC Bangalore, and Naveen will be talking about streamer formation in particle-laden polymeric flows. So the video may be started.
I am Naveen, and here I am going to present about streamer formation in particle-laden polymeric flows. So what do we mean by streamers? Streamers are thin, flexible, thread-like structures formed by irreversible aggregation of colloidal particles and subjected to flow in a polymeric fluid through a suitable flow channel. The name streamer is inspired from a morphologically similar structure observed in bacteria-laden flows. This system of particle-laden polymeric fluid is observed in many artificial and natural processes. Despite their wide occurrence, the exact mechanism of streamer formation is not yet completely understood. Colloidal streamers were first reported in 2017 by Day1 and co-authors. This is the microscopic image, and this is the SEM image of the streamers they have reported using a microfluidic channel for very low Reynolds number flow. Now, with an objective to show streamer formation at higher Reynolds number, we came up with this experimental setup. It is a simple Taylor-Coiled flow with a stationary needle in the angular space to act as a streamer formation platform. And then there is a camera to record the events happening around the needle. We can see that as the rod rotates, experimental fluid flows over the needle and streamers are forming around the needle. We have used ground floor powder as the particles and polyethylene oxide with molecular weight 5 million grams per mole as the polymer to prepare our experimental fluid. Experiments were performed for a total of 25 data points. Based on the visual observation after 30 minutes of experiment, the state observed were categorized into 4 different regimes. First, here is the state of no streamer formation. Then we have type 1 streamers. They are long and sparsely distributed along the length of the needle. Then we have type 2 streamers. They are short and dense. And then we have type 3 streamers. They are long and densely distributed along the length of the needle. All these observations are collected in the form of a streamer formation state diagram. Here we have Deborah number on the x-axis and concentration ratio on the y-axis. We can see that morphology of streamers are affected by hydrodynamic conditions and concentration ratio of polymer to particles. Another interesting observation of our experiment was that streamer formation was observed only when polymeric solution was allowed to age for about 15 days. Freshly prepared pure solution does not show streamer formation. More research is required to unravel this mystery of aging. With this, I would like to conclude my presentation and thank you for listening.
Okay, thank you very much. That was a good presentation on time. So the floor is now open for questioning. All the panelists and the attendees may ask questions. Please go ahead.
Naveen, I have a question. In your, you mentioned with these aggregates, right? In one of the microstructure that you have, you say aggregates.
Yes, sir.
What is the reason for the aggregate formation?
So, sir, the aggregate formation is supposed to be happened by the action of polymeric bridging. So, a polymer chain can adsorb on 2 or more particles and act as a bridge to draw them together, and hence cause the flocculation of aggregation of those particles.
So does it happen when they are in a quiescent state, or does it occur when they're in under flow?
So, sir, here in the streamer formation experiments, they were under in flow, but after that, I tried the quiescent experiment also, and it was interesting to see that I don't see like much difference when there are only particles and when there are particles plus polymer. In the quiescent state, what I got was similar morphology when I observe it under the microscope, optical microscope.
I didn't get what is the concentration of the particles that you're putting in these fluids? What is the particle concentration?
This is a 0.01% weight by weight.
But that's too dilute to cause any of these streaming, right?
Sir, but in the flow I am getting streamers, but yeah, in quiescent I was not getting flux formation.
Okay. Yep. Thank you. Thanks.
Okay, sir.
Yeah. So if there are other questions, please go ahead and ask. Still have some time.
I have a question. Thanks, Naveen, for the poster. I have a quick question. This is very new to me. So you said the polymer, kind of flows on top of 2 of these particles and acts as a bridge, right? So at what scales are these?
So here the particles are around 10 to 20 microns, and the polymers, like radius of gyration of the polymer is in the range of like 10 to the power 2 nanometer.
Oh, okay. So if you increase the polymer gyration length, would you increase the length of these, or will it affect the way the colloids merge?
I don't know, sir. Already this polymer is very high molecular weight polymer. So to increase the chain length of the polymer, basically we have to increase the molecular weight.
Yeah, yeah. So
And
it's already very high, is it?
Yeah, already very high. And I have not tried with any other polymer. Means I have not tried changing the polymer.
Okay, thanks.
I have a question. So, in the aged solution, so have the polymers already combined and formed a chain, and they're just getting linked with this needle, or they're forming the bridge in situ? Because it's taking 15 days for you to see this streamer behavior. So, what is your comment on that?
Okay, ma'am. So the particles and polymers are not mixed before 15 days. It's like polymer solution is prepared, only polymer is there, and it is allowed to age for 15 days. And I mix the particles and polymer just before the experiment. So like aging is not particles and polymers together, they are not aging. It's only the polymer that is like aging.
I see. So if you just take a sampling of the polymer solution, you will not see any of these.
With the fresh polymer solution, I don't get streamers.
So with 15, no, not with streamers. If you just sample a small solution of this polymer, aged polymer solution,
Okay.
do you see any aggregate or something? Is my question.
No, ma'am. It's means visibly clear even when it is freshly prepared, and even after like aging of 15-20 days, it looks same.
Okay, I believe we have time for maybe one more question.
Yeah, Naveen, this is Jason.
Yes, sir.
So a nice talk and good work. Yeah, my question is, do you see these streamers occurring away from this rod, or do they only form on the rod?
So, sir, not on the rod. There is a needle in the annular space.
I mean, sorry, needle. So do they only form on the needle, or can they even form in the free flow?
No, sir, they did not form the free flow, because one experiment I tried was I removed the needle. I had only rod rotating, and then I take sample after like 5 minutes, 10 minutes, 30 minutes, and then I observed it under microscope, and I don't see any aggregate structure. So like needle is, as per my experiment, yeah, needle is required for the streamer formation.
Why is that? You have any explanation for that?
That I don't know, sir, exactly. I cannot say.
Yeah. Thanks, Naveen.
Okay, thank you very much. So I think we have to end this session here, this particular presentation here, and then we'll move on. So the next and the final speaker of this entire session is Chandeshwar Mishra, who is from RRI, and Chandeshwar will be talking about the role of solvent microstructure on the aging dynamics and rheology of aqueous suspensions of a soft colloidal clay. So the video may be started.
Hi all. Today I will be telling you about our recent work in which we have studied the effect of solvent microstructure on the aging dynamics of aqueous electrolyte suspension. So to do that, we have added two types of molecules, dissociating and non-dissociating molecules, in which NaCl and glucose, they actually induce the structure formation in the water. Therefore, they are classified as osmotrophs. And DMF and KCl, they breaks the water structure. That's why they are classified as a zoetrope. And here, NaCl and KCl, they are two dissociating molecules, and glucose and DMF are non-dissociating molecules. Here we have plotted the time scale related to the alpha relaxation process estimated from dynamic spectrum study. So this is for chlorolaphrolate dimethyl, and here in this way we are increasing the NaCl concentration. You can see the divergence happens at a real time once we increase the concentration of NaCl. And also this is the same is in presence of glucose also. So yeah, so here there are two mechanisms. One like the structure formation in presence of NaCl that increases the osmotic pressure gradients, and also NaCl decreases the device gradients. So that's why there is an enhancement in the aging. And in presence of glucose, so the structure formation in water basically increases the osmotic pressure gradients, and that enhances the aging of aqueous electrolyte suspension. And in presence of DMF, we can see that average tau W takes longer time to diverge, means the aging is delayed here. because the disruptive nature of DMF decreases the osmotic pressure gradient, and which basically delay the aging. So in presence of KCl, you can see in spite of being a KO drop, it is actually enhancing the aging. So that's because KCl behaves like similar to NaCl, and to quantify that, we have measured conductivity, and you can see the NaCl and KCl, they have similar conductivity for same concentration. And KCl also decreases the potassium ion also decreases the Day1 screening length. So that's why there is an enhancement in the aging. So next we performed the amplitude tube experiment at the same waiting time, and we can see in presence of NaCl, glucose, and KCl, there is a increase in both storage and loss modulus at same waiting time. On the other hand, it decreases in presence of DMF. So it means NaCl, glucose, and KCl enhances the aging. On the other hand, DMF basically delaying the aging. And next we perform traversal imaging experiments. So this is for pure electrolyte. This is for 1 millimolar NaCl, 90 millimolar glucose. This is for 90 millimolar DMF, and this is for 1 millimolar KCl. And after 24 hours, so we can say they all are forming honeycomb-like structure, but the morphologies are different. So to quantify that, we have measured the pore area, and we can see the pore area is less in presence of NaCl, KCl, and glucose, and it is higher in presence of DMF. Means the system is forming strong gel in presence of NaCl, glucose, and KCl, and it is forming weak gel in presence of DMF. So to summarize that, we have observed that the dynamics of laponite particles depends upon the competition between electrostatic interactions and alternation in the solvent microstructure, and we have seen that the interaction dominates, the electrostatic interaction dominates in presence of NaCl, KCl, which is non-dissociating molecules, and in presence of non-dissociating molecules, the dynamics is completely driven by osmotic pressure gradient, which arises due to structural changes in the water.
Okay, thank you very much. So the floor is now open for questioning. If you have any questions, please go ahead. And I believe the speaker is available.
Yes, sir, yes.
There's a talk by one of the attendees. Sorry, there's a question by one of the attendees. Maybe we can go first with them.
Yes, please. Yeah, absolutely.
This is a nice work. It's very, very good work. So what kind of interactions are present between laponite and the solvents here?
Yeah, so actually that laponite, they have sodium ions around the laponite particles. So actually they form dibilayer, and if you have many of these particles, so they will repel each other. Okay, so that added NaCl will also participate in the dibilayer. So that's basically increases the repulsion. Okay, so yeah.
I'm talking about the glucose and other molecules.
Oh, achha, glucose. Sorry. So in the presence of glucose, the water molecule, they form a structure around the glucose molecule. So that basically increases the osmotic pressure gradients. So this osmotic pressure gradient actually playing an important role here, and that's drive the system in a kinetically rested state at much earlier time.
Is there any preferential adsorption of these molecules onto the clay surface?
So actually, we wanted to study the effect of solvent microstructure and as well as the electrostatic interaction on the aging dynamics. And we found that there are few additives which basically change the water structure. So in that, we have chosen the glucose and DMF and all.
Okay, thank you.
Okay, thanks a lot for the questions. So we have time for some more questions. Please go ahead.
Udipta, can I ask?
So yeah, please go ahead.
Hey, so see the expression that you have for the electrostatic interaction, right? You have this WDL, I think, right? Yeah. So that expression, if you look at the particles that you have, they are like elliptical discs, right? They're tiny discs, and they're elliptical in shape.
Yes, yes.
Now, but then are you really worried about the orientation dependent interactions as well in your system, or how are you modeling the double layer interactions?
Yeah, actually, so it's not like any orientational ordering is there.
So as you increase the waiting time, so what happens?
My question is something like this. See, when you talk about this, see in this expression, e power minus kappa d, that d is the interparticle separation.
Yes.
Right?
Yes.
Now, for a particle that you're considering, it's not a spherical particle, right?
Yeah.
Now, are you talking about the distance between the face and face of the other particle, or is it the face and rim?
Face to face, actually, yes.
Why would the other be not important?
Yeah, so because actually the sodium ions, they are surrounded around the face of these particles. Okay, so it's like, you have two particles, and they are separated like this parallelly. Okay, so the ions are in between these particles.
But if you look at the particle, you had a schematic, right? It says that both the face as well as the rim is charged.
Yes.
So why would you worry?
But actually, the rim has a very less charge actually. So all the interaction dominated by the phase charges.
Okay. Yep. Thanks.
It's like only 10% of the charges which are there on the face.
Okay. Is that from literature or is it from your own data?
Yes. No. It is there in the literature. Yeah.
Okay. Yeah. Thank you. Thanks.
Okay, so maybe we have time for one more question. So there is time for one more question.
I can
yeah,
ask
sure, go ahead.
last question. So
yeah, sure.
So how are you distinguishing this alpha relaxation and beta relaxation?
Yeah, so if you can see on the down left of my poster,
Correct.
So here we have the normalized intensity autocorrelation function versus delay time. Okay, so this we have estimated from the dynamic light scattering study, and we can see there is a two-step decay in the plots. Okay, so this part is basically beta relaxation process, and this one is alpha relaxation process, and we can fit this plot to this double relaxation process equation, and from there we can extract the time scale related to the beta as well as the alpha relaxation process. Both we can extract from here.
I mean, I understand the beta relaxation. What you just said, that rattling of particle within the cage formed by the neighbor. But I am finding a little bit hard to understand what would be the alpha relaxation here. So I mean, is it a two relaxations going on? One is the rattling.
Yes.
And can you explain what is the second relaxation here?
Yeah, there are two relaxation, and as we can also see in the intensity correlation from data. So
I understand the two regimes which you drawn, and I can imagine the first regime, what you said, relaxation. Okay. I'm just trying to get that what are the particle who are participating this second relaxation. What is the corresponding scale?
Okay, so it's like with aging, so the particle actually they're jammed actually. Okay, so here we have particles around like many particles around the one particle. So it's like cage formation.
Right.
So here also the cage formation phenomenon is happening. Okay, so that the beta, that alpha relaxation process is coming from that.
Then what is?
All right. So I am very sorry to interrupt. I'm very sorry to interrupt at this point. I hate to break this conversation, but we are running out of time. So we'll have to end the session here because I believe there is another talk today. So thank you to everybody for attending the session and asking questions. I think all the presentations were really interesting, and I hope that everybody enjoyed the presentations. And I guess we'll see everybody in the next talk. So thank you very much. I guess we can end the poster session.
Yeah, I think the next talk is actually at 5:30. So maybe, I think we could probably take a 10 minutes break so that, people can stretch and join us back at 17:25. That is 5:25 p.m. Alok, is that okay?
Yeah, that's great. I'll just put up a PPT and with the time for everybody.
Okay.
So I'll just make it 5:25. Let's not stop the YouTube thing. Let's keep that running, I guess.
Okay. Hi, Sanath.
Hey, Basa.
Too early in the morning for you? Or is it
No.
normal?
I mean, it's about an hour since I got up, but.
Okay. Okay, great. We'll just wait for a few minutes.
No rush at all. Maria, when do you have to go?
What is that?
Hello.
Maria has to go. I'm just wondering when she has to go.
Yeah, just tell me by someone I need to get started.
Okay. When is your next meeting?
Well, my meeting's in an hour, so that's fine.
You got a little time. Okay.
I have time to have lunch between the two.
Are you guys working from home or not yet?
Yeah, we are still working from home. Yeah.
Hi, Sanath. This is Irshad from. I work in the office.
Hey, Irshad, how are you?
Yeah, I'm doing good. Thank you. I appreciate you joining this early hours. Yeah.
My pleasure.
Basa, when it's my turn, is it okay to share a couple of slides on the screen? Is that okay?
Yeah. Yeah, that would be fine. That would be fine.
Okay. That's brilliant. Thank you.
So, Maria, is there a plan for you guys to go back to work, or is that still out there?
So the office opens on Monday, but it'll be just for people who cannot work from home properly, because the guidance in the UK is very much if you only go to work if you can't really work from home. So workplaces have to be COVID secure, but again, because we are in tier 2, which means that the risk is still quite high here, workplaces are only open in a limited way. So I will be working from home. Yeah.
I mean, we have a real fear now because it's really surging here in the US. And New York has kept it under control. But there is a sense now that even that's going to change. So we're talking about, right now, 50% lab occupancy is allowed. That's going to go down, we think, to 30. I can, in principle, go to work, but I'm not allowed to meet face-to-face with anybody. So it's just sort of a change of scene.
Yeah.
And it's been going on now for 9 months, and it's gotten old.
Yeah. I mean, I don't know if you shared, but yesterday the UK approved the Pfizer vaccine. So actually they're starting to roll that out, starting with care workers and health workers next week. And I think the plan would be that then they move to the vulnerable and they're really old and they start working downwards. But of course, it depends on how quickly other vaccines are approved as well, because this specific one has to be stored at -70. Yep. So that is obviously a concern because not everyone can access, it's not that accessible.
Well, the problem really is that there's been such a rush to this vaccine. All the 3 vaccines we have, they've been rushed through in less than 9 months. You just, and especially the messenger RNA-based ones, you just don't know what you are opening. It's a genie, right? You've opened it up, you go in there. If you can put it back in the bottle, if there's something wrong, you have no idea. It's kind of a very scary moment in many ways. If it works, great. But even the Pfizer one had some issues, if I remember, right? In terms of safety and
So the Pfizer one is also an RNA one, yeah. So we just don't know enough about it, but hopefully it works. So when do you want us to kick off? Are we still waiting for everyone else to rejoin?
No, I think we have about 40 plus audience. I think the number is going to go up, as we speak. So I think maybe it's good time to start. So maybe
so shall I share my screen then?
Yeah, please go ahead. So I'll just take 1 minute and then make some announcement quickly. So unlike last year e-SMYIM, so we do have 2 mentorial talks and it's a great pleasure to have Professor Sanath Kumar as one of the keynote speakers of today of this year's e-SMYIM. And so we'll also have a short intro session by Dr. Maria, who is the managing editor at RSC. So with that, Dr. Maria, floor is yours.
Thank you very much. Can you see my proper presenter kind of view of the slide? Perfect. Okay. It is a pleasure to be here today. As Basa mentioned, I'm the managing editor of the journal Soft Matter, published by the Royal Society of Chemistry, and it's a pleasure to be at this Soft Matter Young Investigators meeting 2020. Soft matter, as most of you probably know, provides a unique forum for the communication of significant advances in interdisciplinary soft matter research, and there's a particular focus on the interface between chemistry, physics, material science, biology, and chemical engineering. The journal's editor-in-chief is Professor Darren Potran at the University of Delaware in the US, and he leads a board of international associate editors and board members. Before I move on to introduce the speaker, I wanted to mention that we have just published a themed collection on peptide soft materials in the journal Soft Matter. And this collection was guest edited by Arindam Banerjee at the Indian Association for the Cultivation of Science and Ian Hamley at the University of Reading. This collection focuses on peptide soft materials in the broadest sense and is free to read until the 5th of March 2021. So if you are interested, please visit either the website here, or you can find it very easily through the journal website, or you can email me or Ershad and we can give you the details. And now it gives me great pleasure to introduce the next speaker, Professor Sanat Kumar. Sanat has been an associate editor for Soft Matter since 2017. He's currently the Barkovsky Professor of Chemical Engineering at Columbia University. His research interests are in the field of polymers and biopolymers, and today he will talk about problem solving defining his professional career. So thank you very much, Sanat, for agreeing to give this talk, and over to you.
Thanks, Maria. So, folks, it's a wonderful pleasure. So should I start sharing? Maria, you want to stop?
I'm just trying to do that. Yes, sorry. Thank you.
No problem. And you can sign off. I got it from here.
Thank you very much. Bye, everyone. Enjoy the rest of your meeting. Thank you.
Hey, folks. So I'm going to get started, right? It's 7 a.m. for me, so it's kind of very slow for, I'm still waking in many ways. And so when they asked me to give a talk, I was sort of torn, because on one hand, I wanted to come and talk to this audience. On the other hand, I may be a little incoherent. So please do stop me. I'd like, rather than have a lecture, to have more of a discussion format. So just jump in, either through the chat box, if you want to just unmute yourself. Is everybody unmuted, Basa, or do we need to do that? Or should they put questions to the chat, or what do you think?
So about, we have about 25 in the panelists who can speak whenever they want. We can also promote all of them to the speaking mode as well. I'll do that.
Doesn't matter, whatever works for you guys. If you want to do that, if you want to just pop questions into the chat, whatever, just let me know, raise a hand, we'll figure it out. All right. So this is in many ways, very special for me for the following reasons. One, Soft Matter is part of this whole consortium, which makes it very good. The other thing I see is that, I see Basa here, obviously, Dilip, and I saw in one of the attendees, I saw Sumesh Thampi was also here. These are people that I have now begun to work very closely with in the last 2-3 years. So I've been visiting IIT Madras every year for about a month or so. And, that was the first time I've started to do that. I graduated IIT Madras 1981. So I've been around this block a few times, right? And so I'm going to give you perspectives from many different points of view. I'm going to talk a little bit about my research. I'm going to talk about my time as a department chair and the lessons that it taught me. And finally, I'll tell you things that I've learned as an editor. So all of these things are going to sort of telescope through each other. But the idea is that, it is wonderful to be back in a forum that is organized by IIT Madras. And for many reasons that I will express to you, the fact that it's focused towards young people also very much appeals to the department head in me, because I will show you that growing my department has been sort of a central focus of things that I did do. Now, the one thing that I will talk you through as I work through my talk is the power and the importance of collaborators. So as young people, you have worked with your PhD advisor, you worked with a postdoc advisor, and now you're just starting your academic careers. And to me, what has been incredibly enabling has been the number and the quality of my collaborators. So Sumesh and I, for example, now have Sumesh Thampi and I have had a project going on for a year plus. And the way we sort of do that is by meeting once a week. That's pretty incredible, because that means either meeting at 7 o'clock our time or 8 o'clock our time on the East Coast, or for Sumesh to meet at 8 o'clock in the night, so that we can, do it in the 10 o'clock in the night our time. So finding times to work together has been hard, but we do it because it's been incredibly rewarding. And so this idea of working with people across the world and getting new ideas and giving them new ideas is sort of been a very central focus of what I've done in my career. Okay, so I'm going on long. Let me start. I always like to start with, and I've lost my screen here. I have no idea what just happened. Actually, I do. I clicked on the Columbia link and it took me to Columbia. Let me go back to my talk. There you are. Okay. So this slide is my university. Okay, and I'm looking from the science and technology part of Columbia University, which is in the city of New York. So this is Manhattan. You're looking straight south on the island of Manhattan. And if you look over to the right here, and can you guys see my arrow key? Can you see my pointer or no?
Yes,
No.
sir.
Yeah, we can.
I'm sorry, what? You can. Okay, cool.
We can. Yeah.
Yeah, so this on the right side, this gray thing, that's a very foggy, this is probably a fall day, and you can see the Hudson River there. This is the Columbia campus, okay? And, you know, the central dome building you see is our administration. I mean, you walk through a university like Columbia and you understand its place in the cultural milieu, for example. So this building you see here is called Pulitzer Hall, and Pulitzer Hall was given to Columbia by a guy called Pulitzer. And that's where every year the journalism awards, the Pulitzer Prizes are awarded. So you walk through there and you see absolutely the very best generation of journalists getting trained. So when you sit here, you know, you just watch people who are going to be the next generation of leaders. And one thing that I've had going through my career, I mean, I went to IIT for my undergraduate, went to MIT for my grad school, is that we've moved with people who have all been leaders. And that's been also a very nice experience, because, you know, keeping in touch with my PhD cohort, for example, has allowed me to understand what the issues are of the time. So I'll come back to that as I go through. This street here is Broadway. I walk about 10 blocks from here to get to work. Central Park is down here in the distance. The point I'm trying to make here is that you sit in a city, you're in a city environment, but it's an incredible place with lots of energy. And to me, a lot of what I think about, what I work on, is driven by the fact that I live in the city. And I'm going to try and illustrate to you how that impacts the work that I do. So if I can ever get this guy to work and not keep going to this webpage, that would be useful. So I want to give a shout out to the people that I worked with. My undergraduate thesis was with this guy, MS Anand, who, as many of you know, later became the director of IIT Madras. MS Anand still comes into work, and when I go into IIT Madras once a year, we spend time, we discuss problems, we always try to work together. And that's been another very big highlight, keeping in touch with my advisors. Guys below, my PhD advisor, Bob Reed, now is no longer alive. Uli Suter, he was at MIT, now he is at the ETH in Zurich. Now, why am I bringing these people's names up? I'm bringing them up because, you know, when you do your PhD and your undergraduate and your postdoc, your advisors always tell you what to work on. So it's very easy in those days to find problems to work on. But then as you go into your own academic career, you ask, how do you work on problems? How do you find problems? There are some people who know exactly the problems to work on. There are other people who always seem to be struggling. So this is a question that I've asked Professor Anand, I've asked Bob Reed, and they tell you something which I would like you guys to remember, which is that if you want to think about problems to work on, you don't have to go look at some esoteric place. Just look around you, right? If you look around you, there are so many problems to solve. And so the problems that I will be talking about are the ones that are of relevance to today's economy, all right? So there are abstract things we talk about, but they're also very real, immediate problems as engineers that we are trying to solve. And give you a couple of examples, you know, with the COVID virus coming through, in the summer, we ran a design workshop for students, and we had about 100 people sign up. This is something we provided as a service to the community. How do you scale up production of COVID vaccine? You also did things like, you know, we figured out, you know, are there alternative vaccines? What's the danger of an mRNA? So these sorts of things became design projects. The students went and researched it. We heard from them, and, you know, thus we understood what might be coming down the pike. And also we were able to offer up ideas to the medical profession. So it's sort of a very symbiotic relationship. And so what I will try and convince you of is that trying to solve what looks like the problems of the times is the way to find problems. And that's really, really critical, because if you can have all the tools in the world, if you work on obscure problems, no one is going to care. So as a person starting out in your career, over and over, I will say to you, you pick the problem. Once you pick the problem, that will sort of drive your career. Okay, it'll drive your reputation. And so take a lot of care, but then don't get frazzled that you don't know what problems to work on. Just look around you. And I'm going to illustrate that through two examples that my research has taken over the last decade or so. The other thing I wanted to tell you is that a lot of this is very contingent on funding. And I've gotten very consistent funding from the Science Foundation and from the Department of Energy. There are also other places that have funded me. But these two guys have been very, very consistent funding me through my career, which is now something of the order of 30 years. So that is another very important thing. You have to establish funding so that you can pay for people that you work with. So those are sort of starting thoughts. And I'm already going long, so I'm going to speed up. And I'm going to tell you about two problems that I've chosen to work on in the last decade or so. The first, everybody okay there? Anybody have a question? Okay. So the first, over the last 15 years or so, my group and I have focused on one problem, which is looking at organic polymers and mixing them with inorganic nanoparticles. The history for this problem goes back to the 1940s. And the first case where people started studying this was in the case of rubber. Okay, so natural rubber, as you all know, is a very important soft material. But if you turn around and think about when you were in school, you looked up an eraser, right? And you used that to erase the pencil marks that you did. What you found was it would erase the pencil, but at the same time, the rubber would wear. You would see pieces of rubber just come off, right? And so the big problem with rubber in its initial form as it came off from a tree was that it was a very important material that you could cross-link. It could be a soft solid, but it was very resistant to wear, okay? And the way that people fixed it in the 40s is to add carbon black. So if you look at your rubber tire, what you will find is that about 50% by weight of the rubber tire is carbon, the other 50% is rubber, okay? Now, apparently adding that carbon to the polymer really helps to reinforce it, reduce wear, okay? And that has become sort of the canonical way of thinking about it. You go talk to the people at Michelin, and I did that a couple of years ago and said, how did you guys figure out this technology? And they said, we don't know. Likely what happened is somebody was trying to cure rubber on top of a fire. The fire was likely a wood fire, and from there, the carbon black got it. So people don't know, but there was a technology that came about because people added inorganic particles to an organic polymer, okay? So that has been sort of a very big enabling technology, and rubber tires, for example, are, a few billion-dollar business every year. So that's sort of the problem that we work in. And this field was going along without too much progress. And in the 1990s, there was a huge development by Toyota. So Toyota used, they wanted to put more plastic things under the hood of a car. And the problem they found was that plastics like nylon, for example, are incredible materials. So next time you have a chance, if you get a nylon fishing line, look at it, pull on it, it will be very, very tough. What does that mean? It's going to take a lot of energy to break the stupid thing, okay? But on the other hand, if you try to build something out of it that's a structure, it's very soft, right? So its modulus is very low, but it's very, very tough, okay? Now, because the modulus is very low, if you heat it up a little bit, its modulus goes down very quickly. And so if you use it in an under the hood application in a car, it deflects very easily, it buckles very easily. And so this is called the heat deflection temperature. And for nylon, for example, at 120 C, which is the temperature they wanted to use, the modulus is very, very low. Now, what the guys in Toyota found is that if they took a montmorillonite clay, which is an inorganic material, it's hydrophilic, they threw it into a nylon and they got it to mix, okay? When they did that, what is shown here on the left-hand side plot is even at a few weight percent, and to get volume percent, you divide this roughly by a factor of 2. So under 5 volume percent of clay, you saw a tripling of the modulus. Not only that, this tripling of the modulus happened at high temperature. And so because of this, Toyota started using nylon under the hood in radiator caps, for example. Okay, so this has been a very, very enabling technology. Now, looking beyond that, if you go look at biology, apparently this idea of using hybrid materials is all the norm, okay? So for example, when you drink milk, apparently every organism converts calcium into a mineral called apatite. It makes spheres of apatite, and typically the spheres are between 5 and 100 nanometers. And what the body then does is it organizes these particles into an organic matrix, and that, it could be any biopolymer you pick. And here is people trying to mimic bone and enamel. And what people realized is that if I take the particles, I put them in randomly into a polymer matrix, then you get something that looks like bone. It has isotropic properties. If on the same hand, you take the particles, you stack them up into layers and you put the layers parallel to each other, that's like teeth enamel. It's very strong in one direction, but it's very brittle, okay? So what am I telling you here? I'm telling you there are many, many, many reasons to consider particles and polymers together. And further, if like the body, you can organize particles into a variety of different dispersion states, that will allow you to tune properties. This sounds wonderful, right? So why am I talking about this problem 80 years after the first application? It's a fundamental problem that you deal with. Most particles you want to deal with are oxides. They tend to be hydrophilic. Most polymers are made out of oil. They tend to be hydrophobic. When you try and mix particle and polymer, you always get immiscibility, okay? Because it's like trying to get oil and water to mix. So in this particular example with Toyota, the way they got miscibility was to take the particle and polymer and extrude it very rapidly, okay? And so you sort of got this non-equilibrium state where it's very hard to see in this electron microscope image. The monopolymer sheets are in the flow direction and the polymer is sort of around it. So you got an enforced miscibility, but this is not thermodynamically stable. It will fall apart, okay? I think somebody asked me, okay, so
Sir,
carbon is organic. Yes, carbon is organic.
No, sir, you talked about mixing inorganic particles with organic.
Oh, very, very good question. Very good question. So what carbon also does is that carbon tends to generally come in agglomerated, okay? And the way these guys, when they burn carbon, it's oxidized in some little form. So it tends to be coming in a form that is like an oxide, and therefore people think carbon black, as used in rubbers, is slightly hydrophilic. Okay, and so what they do is that they when the carbon black is put in, it has an oxide surface, they force the polymers to somehow react with the carbon black, and that's how they get miscibility. Okay, so it is an organic, but the way it is used, it has an oxide surface, and it still falls in the general paradigm. All right. So very, very good question. So I'm talking about generic problems, and in specific cases too, people can play with surfaces, they can play with polymers to get miscibility, but we want to come up with general strategies to afford not only miscibility, but control over structure. So about 15 years ago, Chris Matuszewski at Carnegie Mellon, who is now, from everything I hear, in line for a Nobel Prize in chemistry, my collaborator, Brian Bensowitz, who is now at the University of South Carolina, all these guys started focusing on nanoparticles, and Brian, for example, does RAFT. Chris Matuszewski does ATRP. What they were saying is, look, I take an inorganic particle, if I densely functionalize it with polymer, then basically I can hide the inorganic core, right? I can, for example, I take the carbon black that we talked about. If I could densely graft it polyisoprene, then I put it back in polyisoprene, all I see is polyisoprene. And then you should get miscibility. Okay, and so the enabling technology from 15 years ago is the ability to densely graft particles with polymer chains, and you could control the kind of polymer, you could control the grafting density, you could control grafting chain length, and people could get to incredibly high coverages. Okay, so an oxide surface like silica has 2 hydroxyl groups per nanometer squared. They could go and functionalize up to 1 of them. So you could get to incredibly high densities. And this became a very big competition. Now, what we realized completely by accident is that going to high grafting densities, while extremely useful, is not very relevant, okay? Because if I densely graft the particle surface with chain, all I see is the polymer, okay? For example, now in this thought experiment, let me start stripping some chains off. So if I reduce the grafting density, at some point, what you're going to see is you're going to see certain hydrophilic patches on the particle surface get exposed, and there'll be certain parts that will be covered by polymer chains. So this is the sort of way you want to think about it. Initially, it becomes a Janus particle, then it becomes a patchy particle with hydrophilic and hydrophobic patches. Now, that's really cool because now you've basically exposed the surfactancy of the particle. And once you understand it's a surfactant, and I mean, this didn't happen this linearly, we sort of fell into it in some way. What we found is that, yeah, once you can control the hydrophilic hydrophobic balance, then you can get all kinds of crazy structures. So this is an example here of a diblock copolymer, if you like, a surfactant. Depending on the hydrophilic hydrophobic balance, if the hydrophilic chains are short, then they still want to phase separate from each other. They cannot run away from each other, so they microphase separate. In this case, you get hydrophilic spheres in a hydrophobic matrix, but in a nicely organized manner. And then as you increase the length of the hydrophilic block, you can get cylinders, lamellae, so on and so forth. So we said, look, if we can expose the surfactancy of the particle, maybe we can start to get these particles either to completely disperse or to form interesting structures in the system. And that's exactly what my group has done over the last 10, 15 years. And this is sort of a summary of what we found. This is for one system, but it applies across a whole range of systems now because people have done 20, 30 kinds of systems to date, and they all behave the same way. So to walk you through it, these are 15 nanometer diameter silica particles. This is at some fixed volume fraction. The volume fraction doesn't matter, but I'm just sort of stating that. We are grafting these with polystyrene, but you can graft it with whatever you feel like. People have now changed the core to go to silica, titania, barium titanate, so on and so forth, just oxides in general. There's also metals like gold, okay? And there are two key variables here. One here, which is the key variable that I want you to think about, is the grafting density. And when you have very low grafting density, you're taking an inorganic particle, putting it in an organic matrix, you get phase separation. That's what this TE I'm showing you. You're getting micron-sized spheres. And the reason these things are not coarsening is because the matrix viscosity is so high, it's in a polymer matrix, that it takes a very long time for these particle agglomerates to move and find each other. It's very hard for them to do Lifshitz-Lyasov type ripening, but you are getting phase separation here. On the other hand, if you very densely graft the particle with polymer chains, you completely have hidden the hydrophilic nature. If you put it back in polystyrene, you get this beautiful dispersion here. And this is a TEM micrograph. When you do scattering, you see absolutely nicely that the particles are well dispersed. Now, in between, when you vary the coverage is where you see very interesting phenomena. You see strings of particles show up. You see this sheet-like structure. So you can see sometimes when you look at the sheet face on, it's microns in size. If you turn it around, look at it edgewise, you see this one line running through. That's a couple of particles wide, and that here is a 100 nanometer wide sheet. So you're able to assemble these particles into sheets. This structure here is what looks like DLA. It's diffusion limited aggregation. But the general idea here is just by varying this one parameter grafting density, you're able to get control over not only whether the particle goes in or out, but also whether it assembles into different structures. So now using this, we've started to do a lot of different things. And for example, I forgot to put this slide in here. We asked about the mechanical behavior of this material. And so I'm going to pose you guys a question. If I take a rubber polyisoprene, right, and I put particles in here, which of these states do you think is going to give me the best mechanical reinforcement? Any ideas? The question making sense to all of you? I lost everybody here. What's going on?
And so can you go back to the previous slide?
Sure. Give me 1 second, okay? I'm having technical issues, but we shall see. Yeah, go ahead. What was your question? What was your statement?
Sanath, your slide is not visible.
Is it visible now?
It's not visible.
Give me a second. Let me get organized. My Zoom is really acting up. Excuse me, guys.
Yeah, now it is.
Good. Sorry about that. Have I been showing my slides all this time or no?
No, you have been.
Okay, sorry. Because suddenly my Zoom started acting up. So, the question we asked is, if I take a rubber matrix and I put the particles in here, the general accepted philosophy is that this would be, the well-dispersed state would be the state of maximum reinforcement. That's sort of what we've been taught. But in fact, what we found is that this state here, where the particles are sort of in a DLA-like structure, seems to be the best mechanical reinforcement. And then we thought about that, and this actually makes sense because it tells you if you have a liquid-like material as a background, the particles are what provide strength. And if the particles can percolate through the system, that allows for stress propagation, okay? And so it turns out when your matrix is a rubber, this indeed is the best reinforcing state. Now you go back and talk to people in the rubber industry, and I've talked to Goodyear, and this is what they find empirically. If the particles form these structures that are called fume silica, and if the fume silica particles percolate across the system, that is apparently the state they want. Now they don't know how to control it, but now we know exactly how to control it. By going to the appropriate grafting density, you have control over it. So here is a case where we picked a problem that was canonical, it had application all over the place. We're able to control the particle dispersion state by realizing surfactancy. And then by exploiting surfactancy, we can start to ask questions about mechanical properties. And then we've done lots and lots of work with these systems. But it all comes back from asking the most fundamental question, which is, how do I take something hydrophilic, something hydrophobic, put it together? These ideas exist, but it's just adapting it to the right situation. Okay. Everybody happy so far? I'm going to switch gears. How am I doing for time, Basa?
You have about 30 minutes to go.
Perfect. So I'm going to speak, and I want to give one more example, and then I'll go talk about my non-technical stuff. So we, over the last few years, have been very interested in gas separation, all right? And this is basically coming from the fact that if I look at power plants, for example, you're generating CO2 and nitrogen. You want to separate out CO2 from the nitrogen stream. And similarly, in my country, there is a lot of fracking going on. So we're generating natural gas that comes with 30% CO2. And again, removing the CO2 at every stage is what is deemed to be critical. And we want to do it cheap, okay? There is a plant in Texas that is now trying to collect all the CO2 that it generates. And to do that, they're spending 30% of every dollar they generate power-wise to remove the CO2 from the flue stream, okay? So it puts up the cost of power by about 30%, and that's not acceptable. You'd like it to be in the 1 to 2%, okay? And so a lot of technology is being developed towards using membranes to affect the separation. And what is a membrane? In this case, typically people just take a polymer they found, they spin coat a layer, which is about 100 nanometers thick. And apparently what they've figured out is that if you make a polymeric membrane, just because of the way polymers pack, depending on the polymer, there's sort of a free volume around the polymer chain, which is a couple of angstroms across, okay? It turns out that is enough to selectively separate CO2 from methane. Now, just to give you an extent of the separation here, CO2's diameter is about 3.5 angstroms. Methane is about 4 angstroms. So these polymeric membranes are able to separate 3.5 versus 4, okay? And that's incredible. But how do they do it is completely empirical. What they do is they make a membrane, they challenge it with the feed stream up front, they look at what comes through on the other side, and the way they characterize what comes through is through a flux, okay? And the flux is related to the pressure drop, it is related to a thickness, but the key material parameter here is a product of the diffusion constant times the solubility of the gas in the membrane. The product here is called the permeability, okay? So if you want to get a lot of CO2 going through, which is what you want the permeability to be as high as possible. And then you want the membrane to be selective, right? And so the ratio of permeabilities is called the selectivity, and you want that number to be as high as possible as well. So this is the technology. And the way people do that is they just go find random polymers, throw it in there, see what happens, okay? And so over 40 years, people have acquired a lot of data. So every point you see on this plot is a point for a different polymer, okay? What is plotted here is the permeability of CO2 along the x-axis, the selectivity, CO2 to methane. There's about 700 data points here. That means some idiot went to a lab, tested 700 polymers, okay? And then by doing that, they found out that as the material got more permeable, that means these holes got bigger, and you can achieve that by having polymers that pack worse and worse. As the permeability went up, the selectivity dropped, okay? So we know that empirical knowledge, and we know that there's sort of a line here called the upper bound, and there are no polymers that exist above the upper bound. So if you really want, you want to be up here. You want to have high permeability, high selectivity, because that means you can get a lot of CO2 through without losing any of the nitrogen.
Excuse me, sir, I have one question.
Absolutely. Go ahead.
So yeah, I'm Umaya, sir. I am from IIT Madras. So
Wonderful. Yeah. What's your question?
yeah, I am preparing some membranes out of some polymers, which is water responsive polymers. Here my question is, you are saying that your membrane will be selective towards carbon dioxide.
Yeah.
But it should have some functionality which especially will selectively separate the carbon dioxide. So
No, that's the beauty of it, right? So what people have found is that, some of these polymers have absolutely no selectivity. Okay, you talk about solubility selectivity, right? The way people think about these membranes here are not as a solvent selective, right? It's more selective based on size. So it's like a jali or a sieve is what they think about. Okay, so if the molecule is smaller than the sieve, it
selectivity in
goes
the
to.
sense, excuse me, sir. Selectivity in the sense, if you have mixture of gases, out of the mixture of gases, you have to choose one component which selectively you can separate out from the mixture. That membrane usually used to do.
Right.
Here you are generally specifying. I mean, you are generally talking about a polymeric membrane. So you can separate based on the size of the effluent. So depending on the size of the component in the mixture, they can separate out. Now in the polymeric membrane, based on the polymeric chain, they can separate the component in the mixture. But if you have some functionality in the polymer chain, then it would be better to selectively separate the component which you would like to separate.
You're absolutely correct. You're absolutely correct. And I will show you examples of that. But if you go talk to the people working in the membrane field, they will tell you this is absolutely correct. But
Yeah, I just
what everything is doing is civic. They're just doing it based on size. And the point you're raising, I will come back to in a minute. Okay? It's a very, very good point. The essential idea that she's bringing up is that I'm only talking about as a size selective, maybe by functionalizing the polymer so that you also use the solubility angle as a tool for selection is understood but hardly ever exploited. Okay. But what I wanted to take you guys to take away from here is that there are 700 polymers people have tested. It's very tedious. And if you, for example, wanted me to tell you which polymer falls where and what is the relationship between the structure of the polymer and its selectivity or solubility, people don't know. There is no ideas whatsoever. So there is need to understand better what the structure of a polymer, its ability to solubilize a gas affects its permeability and its selectivity. So that's sort of an open question. The other question is, people have tested 700 polymers. If you go look, there are apparently 12,000 known homopolymers that have been synthesized. Then there are copolymers, there are mixtures. So we'd like to find a way by which we don't have to test all these materials. We'd like to find materials that go up here, but without doing all the testing. Okay. And so what we decided to do was adapt a new tool, which is available to everybody right now, which is machine learning. All right. So we said, okay, let's start out. Every polymer is made up of monomers. You go look at a monomer, and then it has carbon, hydrogen, oxygen, whatever. So we just said, let's understand if there's any relationship between permeability and the stoichiometry of the monomer. And that we did machine learning, we found absolutely no connection. Okay. So then we said the next level we can look at is sort of understanding the local structure of the monomer. So not only how many carbons, hydrogens, oxygens you have, but also the way they are connected. So these things are called SMYIL strings. And so every group in the monomer of a polymer chain is, you look at the connectivity and you say how many of those groups you have. So you basically have a connectivity vector that characterizes the monomer of a chain. So what machine learning does, it sounds wonderful. It's kind of incredibly dumb. It says there is a linear transformation between this vector of the connectivity of a monomer and the permeability. And so a linear transformation is a matrix. Okay. So what you do is that you take these 700 polymers that you have and you train the machine learning. So that means basically you figure out the best matrix that allows you to go from a vector of monomer connectivity to permeability. Okay. That's all it is. You optimize it over those 700 chains that you know. And then once you have that, you can predict, based assuming that this matrix is accurate, how an arbitrary polymer would behave, right? And so that's exactly what we have done. So if you go back, this is the data we started out with. It's permeability, selectivity. These are 700 known polymers. We trained our machine learning model. We trained our permeability, selectivity, and solubility. And machine learning on this. And then we predicted on every known polymer. So you can see here, this particular graph is again permeability versus selectivity. It's CO2 methane. And this line here is the very best polymers that exist today. And you can see there are many, many more points because now I'm predicting across all the polymers that are known. Now, what you find is that most polymers fall below the very best that we have, and so there's not much use. But if you look, there's of order 200 points that fall above the line. So it tells you there are polymers that have already been made that are better, but they've never been tested in this context. Okay, and so we picked two of those polymers that were predicted, this blue cross and this red cross, which correspond to these two polymers. The machine learning predicts they should do much, much better than what exists. And these error bars are real. These are what the machine learning tells you the error bars are on your prediction for the permeability and for the selectivity. Now, just for the person who asked me this question, if you go back and look here, you've got sulfoxides in here, and the sulfoxide is very important because they love to solubilize CO2. So if you look at this one, you say, this actually works because not only is the stiff chain giving you larger free volume, but the sulfoxide preferentially solubilizes CO2. And so the machine learning is able to pick up on the fact that maybe optimizing permeability it requires you to not only improve diffusion, but also improve the solubility. So these are things a posteriori we understood, but the machine learning picked out and said, you guys should go test these two polymers. So my collaborator, Brian, went in, he made these polymers, we tested them, and the data we got for the blue cross is the blue circle, for the red cross is the red circle. It's within the error bar of the machine learning prediction. Now, to me, that is incredible because the machine learning is incredibly dumb. It just says between the monomer structure and the permeability, you assume there is a linear transformation. I have no idea who died and told us it was a linear transformation. We assumed it, it worked. Okay, so machine learning, I think, is an incredibly powerful tool because now it tells me rather than go and test all of these idiotic polymers, we should now selectively go and look at these few materials because that's probably where the action is. And then, of course, as the question person asked me, it appears it's not just sieving, solubility is an important handle as well. It's telling me obvious stuff, but it's something that people had not thought about. So again, what am I telling you? Just going back to where I started, I'm working on a problem that's germane. CO2 is a very big deal in terms of global warming. Machine learning is a very big deal all around us. This is just taking those two tools and adapting them and saying something profoundly important about separation, about CO2 sequestration, okay? And so this is sort of what I would encourage you to think about is, develop the tools, but always keep your eyes open on the problem at hand. And if you do that, you will have tremendous success. So we've done lots of stuff with this thing. I don't want to talk about it. I'm going to stop and now move to a different perspective. If you guys have any questions, please ask, but otherwise I will keep on going. I'm at 40 minutes. I'm going to talk very quickly and get over in the next 10 minutes. I was department chair for 6 years. And, there are a few things that happened during that time that I want to very quickly go through. So I walked in to Columbia in 2006. And when I walked in 2006, the department had faculty of 8. We had 1 woman, okay? And in the US News and World Report ranking, we would rank number 64 out of 128 departments. The reason that happened was the Ivy League schools really think of themselves as bastions of liberal education. And so they thought engineering was really not something that was a big deal. I mean, very much in contradiction to what we think about in India. In the US, engineers are looked down on. It's seen as a middle-class profession, and the Ivy Leagues did not want to be part of the middle class, so they wanted to get rid of engineering. And then in about 2005, Harvard realized that engineering may be a way forward because people like Intel, every Intel plant costs $4 billion, and the chips they make have revolutionized the way we live. So there's been a turn back towards engineering. And so now the Ivies are putting money back into the engineering. But at that point, when I joined Columbia, was the low point. We were ranked outside the top 50, and that's kind of a disgrace. This is what it looked like in 2009. Okay, we had just before I took over, we had 8 faculty. We had 2 women out of that faculty. Okay, now over the last decade, we've gone from there to 20. Okay, and if you look at this, something that strikes you is that out of the 20 faculty, you see 1, 2, 3, 4 women. Okay, that's 20% women. If you notice, there are two Indians, there's Venkata Subramaniam and me, both of whom come to IIT Madras very regularly. But apart from that, there's no person of color. Now, why am I bringing that up? I'm bringing that up because if you look at our undergraduate classes, they tend to be 50% women, 50% male. And, Columbia is ranked number 4 in the country for undergraduate. So we get the very best students, and they look up and they look and they see no women teaching or very few women teaching. That has become a problem. The second thing we find is 30% of our classes are underrepresented minorities. That means Blacks, Latinx people, right? And on my faculty, we have nobody Black, we have nobody Latinx, okay? This is a deep problem, and you guys have heard about Black Lives Matter and things like that. There is a huge push to try and balance the faculty so that it looks more like the student body that we look at. Now, why is that important? So when I was there, we had one woman, we hired Faye McNeil, and what we found was that every undergraduate student who wanted to do research went to Faye. And the reason for that is twofold. One is I think there is a history that men have treated women badly in STEM, and there's reason for that. The second thing is people relate to people who look like them, okay? And so in the last decade or so, there has been a huge push to add more women, but now there is also a push to add underrepresented minorities of various kinds. And that I think is very, very important, because if you don't educate people who look like you, then you don't uplift those classes of people. In the US, what that has done is created a deep polarization between the rich and the poor, because poor people generally tend to be Black, Latinx. And now you can see that play out by the election of people like Trump, and that's showing a very big social breakdown. And so the way to fix that in the US, we've decided, is to educate people who do not have education. And I think that's a very important lesson for you guys sitting in India, where the social polarization is a very, very strong thing. And what is happening in the US is going to happen there. And to educate people who look different from the traditional IIT person or the traditional engineering student or the traditional student at IISc is an important responsibility that we have. So you guys are the next generation of leaders. Please keep that in mind. It's very, very important that we educate people who look like the people that are funding us. A second point that I think is very, very important is the power of mentoring, okay? So at Columbia, we mentor people because we wanted them to get tenure. So when we hire people, for example, when we hired Ali Obermeyer, who is up there, I'll get to it. So Ali here, she had 6 offers from across the country. She chose to come to Columbia because we were in New York. But what that tells you is that she's a very popular commodity. And if we don't take care of her properly, somebody else will make her an offer and take her away. So we've been very focused on mentoring people. That means meeting with them, making sure things are going well, making sure they get well known, making sure that they are successful. Because if they become successful, then they will give you some credit for that, and thus not only improve our institution, but also stay here, okay? Now that's, for us, the reason to mentor. If I look at India, I think you guys need mentors too. But your mentoring is very different, okay? What I find is that many scientists and engineers who work in India are known within India, but not known outside. Now, what does that mean? That means that if you send a paper to me in soft matter to get reviewed, when I send it out to people for review, they don't know who you are. And so that affects adversely the way the paper is reviewed. Now, is a paper review supposed to be fair and unbiased? Absolutely. But when I get a paper and if I see the author and I know the author, I'm going to say, if they make a mistake, that likely it was just an error. I'm not going to reject the paper. I'm going to say, hey, dude, you made a mistake, fix it, right? So when I get papers from India and people are not known to the community, then the reviews they get are generally a whole lot harsher. And I think the fault is twofold. If people don't know you, it's of course our fault that we don't know you. But on the other hand, we feel we don't need to know you, right? So you guys sitting in India, you really need to find mentors here in the US or across in the world, so that they can help to get you known better. Because once that happens, then things like invitations to conferences come naturally, and that's sort of a self-fulfilling prophecy, because then you get better known, and as you get better known, your work becomes more and more accepted. Now, I'll give you an example here. Guru Kumaraswamy, who I think the world of, he's a collaborator. he just generally does not get invited to conferences. So a few years ago, I had him invited to a Gordon conference. He came in. Nobody knew who he was. He got his PhD at Caltech, but no one knew who he was. He gave a talk, and it was the best talk of the conference. It was incredible because people didn't know about it. They were blown away by how nice his science was. And that has been a kick for him. Now, I'm not trying to take credit for it, because for me, exposing Guru to that environment was good for the environment because we wanted to know the class of work that is happening in India. But on the other hand, the fact that people didn't know him is because nobody was there to push for him. And that can be fixed if you have mentors. So, there are many people like me who go back and forth to India every year. Find us, talk to us, find out how we can help you. We really want to help, but we don't know who to approach. So it's your job to go out there and find the mentors. They will get you the visibility that you need across the world for you to have the impact that you deserve. Now, the other thing I will tell you related to that is that if you talk to people abroad, then it's a two-way street, right? You tell us what the problems are that are important in India. And for example, Swachh Bharat is something that's a big deal in India, right? So maybe we can use that to come up with problems of relevance to India and come back to the US, come back to the UK and tell them, these are the problems that are important. So we are always looking for problems to solve. And so starting to talk to people abroad and getting them as mentors is a two-way street where you find out what's important, we can find out what's important, and that way we help each other out. Okay, so but this I think is a very big deal. You guys should go out, seek mentors. Another thing to get known, and I think you really, really need to get known because otherwise your papers do not get reviewed properly and your funding proposals don't get reviewed properly, is write review papers, right? But that means you approach a journal, you say, I want to write a paper on a particular topic, and then write a paper that is really a review paper. Write something that goes across the field. If you write a highly cited review paper, then that gives you natural visibility. Okay, but don't do that randomly. If you want to write a review paper for me, come talk to me, get my approval, and then write a paper that I will then push for. Okay, because otherwise I get 2 review papers a month that I'm asked to take care of in soft matter. Most of them are crap because there's just people pushing their own work. That's not going to work. Okay, you want a paper that really does go out and emphasize what is known across the community at that point. And that way everybody notices the article, it gives you the visibility that you're looking for. So just to summarize, I think this idea of mentoring is all about visibility. Another thing that I think is really key is proposal writing. And this is an art form, right? When I started writing proposals, I thought the key to writing a good proposal was having a killer idea. Okay, that's really important. I don't deny it.
If I may interrupt once.
Absolutely.
I had a question for you. That's slightly off the topic that you're discussing. You're an editor of software, so I thought it might be worthwhile to bring it up. As young researchers, we are always asked to publish papers in the proper forum. And one of the things that I've noticed, and please correct me if I'm wrong, but some of the classical journals like Langmuir and the Soft Matter, they have lost ground in the last 10 years compared to some of the other journals. For example, Poloid, there are some of the Poloid-centric journals, which seem to have gained ground quite a bit. As a young researcher, I just would like to understand why that is happening and what is your take on this?
So I think there are two things that are happening, right? Two very different things that are happening. One is the nature empire, right? They've just gone crazy. They have a nature for everything, okay? And that, now if you think about it, Nature Communications, for example, you have to pay $5,000 to publish in there. Its impact factor is no better than ACS Nano. ACS Nano has a higher impact factor than Nature Communications, but people will still publish in Nature Communications because of the Nature name, all right? So there's nothing you can do about that. That's just nature and science doing their thing. The other side is there's just a proliferation of journals. ACS has gone nuts. RSC has gone nuts. There are so many journals out there. If you keep increasing the number of journals, the impact factor of a particular journal is going to drop. There's nothing you can do about that, okay? The third thing is there are unethical practices. So there are journals that will focus on accepting papers that they think will improve their impact factor and do all kinds of stuff to manipulate impact factors. So what that means is that, for example, the classic example is colloid and interfacial science. Their impact factor has gone from like 1.5 to 7 in the last 5 years. I still don't read that journal, but what they did was they got a bunch of papers that are highly cited. So my general idea at the end of the day is I'm not going to pay any attention. I think there is a role for classical society journals like, Soft Matter, Langmuir, Macromolecules that, go beyond the immediate. So I still feel like if I publish a paper in Macromolecules, people will read it. It will go to my core community. They will read it. So, as a young person, and I'm going to come to that in a minute if I have the time, is I would not worry so much about impact factors because they're going to come and go. And the future of publishing is really unclear because, as we increase the number of journals, we keep talking about impact factors when we talk to our RSC people. And for example, Soft Matter has gone from 7 to about 3 in the last 10 years. And now it's turning around. It's going to come back up. But it's really hard to sort of work in an environment where everybody is trying to expand. There are more and more papers getting published. People read less and less. So I don't know what to do. I mean, I think you just, at this moment, all you can do is get your papers published in the most appropriate forum and hope that people read it and cite it. Did I answer that question?
Yeah, thanks, Anand.
Sure. I'll come to that in a minute, okay? But I do want to talk about proposals, right? Because to me, this is really important. You think writing a killer idea is what is important for a proposal. That's absolutely critical, okay? But when I sit on a panel, I'm going to look at 30 proposals, okay? Each one is 20 pages long. I don't have the patience to read 600 pages. So what am I going to do? I'm going to read the abstract and I'm going to read the first page. And if you've lost me in those two, I'm not going to read the rest of the proposal. So what I've told every one of the people, junior people in my department, is you find somebody senior like me, I will read the proposal, I will read the abstract, I will read the first page, and if I'm really patient, I will read the last page, and I will work really, really, really hard on those things so that it really, in a very key way, tells the reviewer what the proposal is about, why they should be excited. Basically, those 2 pages are where I am going to put in enough material that the reviewer can take pieces out of it and write their review. So I want the first and the last page of the proposal and the abstract to have the review that the reviewer can write, okay? That's really important. It doesn't matter if the remaining 13 pages are good or bad, because if you don't pass that first cut, nobody gets to read the other 13 pages. I mean, once you get past the first page, then you better have everything right. But the focus that I've taken on is really look at the first part. And so there is a program in the US called the Career program, which is given to junior people. And I worked with a lot of young people on that. And I think basically I have a 100% record on that. So every time I edit it, I work on the abstract, the first page, and that seems to be enough to get it through the door. And then people will read the rest of the proposal. So please find a senior person, focus on those aspects. That's really, really critical. The other thing, break down your proposal. Don't make it densely text. Have figures, have tables. If you have a table that says, these are the experimental systems I'm going to look at, that goes a long way. It appears like you're really organized, you've thought about stuff. And most times I throw in a table at the last minute just to sort of focus the reviewer's attention. You're trying to break the monotony for the reviewer, okay? Do everything in your power so that you write the review for the reviewer. That should be the way you think about proposal writing. And if heaven forbid, if you get turned down, most times people will bitch about how a reviewer didn't read the proposal. That's probably true, but the fault is yours because you did not give them reason to read your proposal. So whenever somebody makes a comment saying you didn't do this or you didn't do that, first get upset, then realize it's not their fault. It's your fault for not making that point clear. And when you rewrite the proposal, try to focus on those aspects. Take these comments seriously, even if they sound insane, because in the end, it's telling you you're not communicating anything or you're not communicating a particular point, and that's why the review was the way it came up. Guys, I'm really running short on time. I don't want to spend a lot more time here. I want to end up with the editorial perspective. I've already talked about this. There's a huge sense of impact factors. I don't worry about impact factors. I send my papers to what I think are relevant journals. Whenever you send a paper to me, always suggest referees. And you have room for up to 6 referees. I will typically get 2 to 3 reviews. Out of them, 1 will be a person you recommend. And if that person is a good person, and if they give a solid review, I will take that seriously. Most times the reviews you suggest, and I don't mean you specifically from India, I mean from across the world, the people they suggest are their friends who don't give good reviews. So if you can suggest people who could give good reviews, that will help you a lot in terms of papers getting accepted. And the last 2 points I'm going to sort of illustrate with some examples. Once it gets reviewed, you get referee comments. Please address the referee comments, okay? And I'm going to share with you real examples of what happened. So here is somebody who sent a paper back to me. It went out for review, and the reviewer said this: the author still did not address most comments from the 2 reviewers. And then they went on to say, therefore, this paper should be published elsewhere. So what they have done here, they are not commenting on the quality of your work. They're not commenting on whether it's relevant. They're not commenting on whether the paper is appropriate for soft matter. They're basically saying, you didn't listen to us, so send it somewhere else, okay? So this is really key. When a reviewer says something, please make the change, even if you don't like it, okay? Because if a reviewer says, you didn't listen to me, go elsewhere, then as an editor, I have no chance. I have to accept that. And this is most often the reason that people get their papers rejected, is because they did not listen to the reviewers. So please always, always listen to the reviewers. This is at the bottom, the 2 paragraphs is what I wrote to a person who sent me a paper. Basically, they did not listen to the reviewers. And I said, if you don't listen to the reviewers and the reviewers tell you, we don't want the paper, there is nothing I can do as an editor. So don't put me as an editor in a bad place by not listening to the reviewers. So this is the biggest mistake people make. Don't make that mistake. So suggest good reviewers. Once you get the referee comments, take it very seriously. The third thing is, don't whine. Don't bitch to me about how you got treated unfairly. There's nothing I can do. I get the paper. I'm a middle person. I send the paper to a reviewer. If 3 out of the 4 reviewers says your paper sucks and should get rejected, I have nothing I can do about it. Okay. So here is somebody that some of us know, and I'm not going to tell you who these people are. Somebody writing to me personally saying, please don't reject the paper. It's a nice piece of work. Look, I understand. You're my friend, okay? But by writing me a letter like this, you're putting me in a very difficult position, because if the review comments tell me I need to reject the paper, I have no option. But if as a friend you put pressure on me to accept it, it puts me in a position of conflict. Well, how did I resolve this? I handled this paper. This paper actually got in. But I've told soft matter, if a paper comes from this author, please don't send it to me to handle, okay? Now, by doing that, you've basically created a situation for yourself where you're not doing yourself any favors, okay? So please do not put unnecessary pressure on me, because, on the next slide, I will tell you there are people watching over me too. So if I try to have an undue say in a paper where if reviewers say reject and I accept it, somebody will be on my back. So I can't do that. Don't put me in a position of conflict. Second thing, here is somebody who wrote to me. This is about a week old. I got 3 reviews. 2 out of the 3 reviews said reject. And this person says, we think the third person purposely rejected the manuscript. I mean, come on. Maybe that's true. Maybe that's not. But to say that doesn't help me in any way. If you have a technical reason why you think reviewer 3 was wrong, state it. Okay, we will go through it. We have an appeals process. We will consider it very seriously. But to just say the third person doesn't like the way my face looks is not a good reason for me to reconsider your paper. So, and when 2 out of 4 reviewers or 2 out of 3 reviews say reject, then you better have a damn good reason why 2 out of the 3 are wrong. Because when I go back, I'm going to go back to the 2 or 3 of those reviewers. They're going to likely say reject. I'm going to take all the comments. I'm going to go to somebody called an adjudicator who's going to see everything. And you better have a compelling reason why that those 2 people before you were wrong, right? So be careful when you come back to the editor. Try to be technical, address the technical issues. And if people are saying reject, please have solid reasons why I should overturn that, because without that, we can't do anything about it. The third thing is, here is somebody who's doing something which is totally unethical. If you read this, it says, I'm writing because I find that there is a reviewer made some comments, and this is very much like their publication that just appeared. They're trying to tell me to disclose to them, an author, who the reviewer is. I just cannot do that, okay? It's an anonymous review process. You may hate the review, but don't put me in a position where I have to tell you who an anonymous person is, okay? So these are all obvious, but this happens enough times, maybe once a week, that I'm telling you don't do that. Because if you do that, I will likely not want to see your paper in the future. Not because I don't like you, but because if you put me in a difficult position, I'm going to just say it's a conflict of interest and send you off to somebody else who's likely to be a lot less sympathetic. Basa, my apologies, I'm way, way, way over, but I just wanted to end on this point that as much as I think I'm an editor, people like Maria are looking over me. And, here is a paper that had 2 referee reports that both said reject. One guy was conflicted. He should not have reviewed the paper, but he did. And in the confidential comments to editor, which is a section only I see, they went through a list of technical reasons why the author over the last 10 years has been trying to publish papers that are wrong. And on that basis, he thought this was the 11th paper in that series. And since the 10 before were also wrong, the 11th one was also wrong. So I found 2 negative reviews to be persuasive. I rejected the paper, but these guys watched over me and they said, look, you cannot take anonymous comments that you cannot share with the author and use that to reject a paper. So they made me go get 3 more reviews and all 3 said reject. So I got 5 rejections on this paper before I could turn it down. So what I'm trying to tell you is, as an editor, even though I have a lot of control, if I ever stray away from doing what is ethically correct, there are people watching over me and who will tell me I better go back and fix it. So yes, blame me if you don't like my decisions, but understand that I'm part of an ecosystem where everything I do is being looked at. And so there is many, many layers of protection. So suggest to referees, answer all the questions, but in the end, if the outcome is not what you like, please understand you can still go to adjudication, but it's not in my control. A lot of times I'm doing what the community wants me to do with the paper. It's not just me talking. All right. Sorry, I went way over. I love listening to my own voice at 8 o'clock in the morning. I'll stop. If anybody has any questions, please ask me questions. I'll be happy to answer them.
Hey, Sanath, thank you for...
Really, my apologies going over.
So I think before we take question, maybe Irshad wanted to say a few words. Irshad from RH.
Yes, indeed. Yeah, I mean, first of all, I would like to thank Professor Sanat Kumar. But I actually didn't intend to speak, but I am really, I don't know, I'm really impressed by the kind of stuff that he just spoke at the end of his talk. I mean, especially, I would say that I haven't seen any better advocate or brand ambassador for a journal, not just for Soft Matter, for any journal for that matter, for publication processes as well. So I really like the way you put up the inclusion and diversity part of things, as well as the need for Indian researchers to have mentors and to create more visibility. I really appreciate that thought. I mean, the idea that you kind of wanted to bring into the Indian researchers. Really appreciate that. And one point that I think I don't know who asked from Susmita's. I think I don't know whether it's Alok or someone who asked the question about a couple of other journals picking up. And I think we as RSC we are moving away from impact factors as a metric. I mean, not just to talk about it's not. I'm not saying that impact factor will be taken away or something. It will still be there as one of the metrics and not just the sole metrics. Probably some people would want to call it as a necessary evil at this moment for this matter. So we have signed the DORA declaration, the San Francisco Declaration, which we are trying to move away from a sole metric like impact factor and also talk about other factors which include the quality of the papers. So I'm again once again thank you, Professor Sanat Kumar, and doing this talk early in the morning for you, and also for Royal Society of Chemistry and Soft Matter Journal to be associated with this particular meeting. I think we have been associated with the Young Investigator Meet, Soft Matter Young Investigator Meet for the last couple of years. We were part of the event last year that you had in Shillong as well. So we'll be continuing to do that in the future, next coming years as well. So please feel free to get in touch with us with either Maria, or even if it's anything specific related to the papers, probably to Professor Sanat Kumar or even myself, if you want to know anything about the journal. And I really, I'm really happy to have engaged with this community. And thank you once again, Professor Sanat, for this exciting talk.
Guys, it's 6:30 in the evening for you guys. If you need to go, I fully understand.
No.
I will offer you an open invitation. You can find my email address on the Columbia website. I'm really deadly serious about this idea of mentoring. I think, I've been coming back to India now very regularly for the last 10 years. And it's very important to me that I give back to the country that bred me and brought me to where I am in my life. And so I'm committed to helping people from there in any way in which I can help you guys. reach out to me and I will do what I can. I mean, that's an open invitation.
Sure.
And if I don't respond when you send me an email, send me another email. It's not deliberate. Sometimes we get overwhelmed, but I am very sincere and I will put you in touch with people if I don't know the answer to a question.
Sure. I think rather than your subject, I think, you know, the kind of the talk that you gave at the end regarding mentoring and proposal writing and you know, need for young people to write more reviews and stuff like that, creating visibility. I think, you know, we would, I mean, we in the Sense RSC, Royal Society of Chemistry, would be more than happy to probably once the situations are conducive, you know, we would be happy to, you know, sponsor one of your trips to India to see where we could, you know, engage you with young researchers and make it a fruitful trip.
Okay, Irshad, then thanks so much. You know,
Thank you, Basa.
Yeah, so maybe we'll have people ask questions if there are some.
Basa, I have one question.
Yeah, Dilip, go ahead, please.
Hi, Sanath. It's nice stuff.
Thank you.
And with all this knowledge we got, I have one question regarding the machine learning. What is the thought behind assuming the linear relationship between the monomer structure and the permeability?
Nothing. It's just trying. There's no logic.
No logic.
You know, you just say, we started out by just using, you know, I mean, the question you're asking is, why did I do that, right? And is there a logical way of picking the minimum amount of information? That's what you're asking, right?
Yes, yes.
And I think that is a field that people in the theory of machine learning are thinking about. And that's what begat things like deep learning, right? Where the system tells you what you have to, I mean, the algorithm tells you what information it needs to predict a property, right? With the kind of physical systems we deal with, we don't have enough data to do deep learning. Okay, so we can't figure out what the relevant parameters are. And so what we do is we do some sort of dumb deep learning where we tell it, this is the chain structure. Let's see if it works. If it doesn't, then you make it a little bit more complicated. So at the moment in the physical sciences, there is so little information out there that it's still very empirical. And eventually, if we have enough data, then we can start turning it. So for example, when you have an electron microscope image, right, trying to identify particles, now we're able to do deep learning on that because there's a lot of data available. And so it tells you what you need. It will look at images and figure out what about the image it has to use to figure out if there's a particle or not. But at the moment, because we don't have enough data, it's a very empirical process. Does that answer your question?
Yes, it does. So just a follow-up question. So deep learning is the next step of this process. Right. So what would be the next step? I mean, you got success already in this, right? Whatever prediction. So there's no need of deep learning here in this context.
Well, it's not true, right? Because I got lucky and, you know, I sort of picked the connectivity of the monomer. But if you think about a polymeric chain, right, there are other parameters. There's chain length that's important. There is, you know, stereoregularity. There's, you know, variety of other properties that I've totally ignored, right? Because I'm only telling you at the level of a monomer. And the reason polymers are special is because they are connected. And that connectivity is completely lost. So, you know, at some point, this is going to fall apart. It's just for this particular property, it worked. So no, this is by no means a solved problem, because I think if we start going to other properties, this idea should fail, and finding where it fails will teach us more. But right now it feels very much like an empirical process without any rules, without any logic. And that's what disturbs me about what I'm doing.
Yeah, thanks a lot. Thanks.
Sanath, Divya,
hello, Professor Sanath. This is Divya here. Very nice talk. Thank you for a lot of information you have given today, especially in the second part. I have a question slightly different from what you have spoken in the second part, because as young researchers, we have a lot of pressure in our initial years to publish. And so what would be your advice on how should we choose collaborations?
I think that you work with people, one who will bring a skill that you don't have. That's how I always go. And the second thing that's really important is when you publish, they give you the credit. So if you're going to go work with a collaborator, likely it's going to be a senior person. And when you work with a senior person, you find somebody who's not going to say, this is my work, and just subsume what you do, because then you don't come out ahead. Okay. So I think it's somebody who, one, has a skill you need two, is able to work with you and not take all your credit. Those are the two things. And third thing, which if you can get even better, is they push your work for you, you know? So that takes a very special thing. It's easier to do when you're more senior. But, you know, I've always collaborated with people, and people will come to you the moment you write one or two papers and they start having some impact. People will start working with you. It takes a little bit. The initial year or two is hard, but that's where you have to just sort of go with your core strengths and publish the first couple of papers in solid journals. And then people will come to you because they see your papers, they have reviewed your papers, they've, you know, they start to see you in various forums. And then when you go and approach them, they will work with you.
Okay, thank you.
Sorry, Bas, are you asking a question or are you going to say something?
Somebody else was asking a question. I just cut them because Devya had,
Hi, Shanat. This is Tarak here.
Hey, Tarak.
Hi. So it's a nice talk. Thanks for this insightful views of for writing proposal and mentoring and diversity. So I just thinking about if I look into your work, you have kind of diversify yourself in doing both theories and simulations. In your early days was mostly they are concentrated on theory and more of molecular dynamics level calculation. So as a young researcher, how you try to kind of navigate in different directions, if you can share some thoughts along those lines.
This is a very, very important point, right? So I've always done theory and experiment. So when I started out, my focus was getting papers out, right? Because that's how you get people to know you. So it was very deliberate that in the beginning we did theory, okay? Because then you can get the first 3, 4, 5 papers out in the first couple of years, and that's what's important. So people to know progress is being made. At the same time, there were students doing experiments, okay? But it took 2, 3 years to get those experiments to a certain point. And at that point, the people doing the experiments were inspired by the theory. So at that point, at the end of 3 years, we could write papers saying the theory predicted this, the experiment found this, either it agreed with the theory or it had improved the theory. So then it became very quickly a symbiotic relationship, okay? But for me, your focus, so I did 2 things when I started my career. I picked problems that were small, where I almost knew the answer, okay? And then I did theory on those problems. So it was doing something which I knew would work on a problem for which I knew the answer. Okay. So do the simplest thing, use that, and then you think you know the answer. When you actually do the calculation, the answer is different. Then you do an experiment. The experiment comes out with a totally different thing. And then it goes from there and it builds. But for me, what was key was doing both. Because if I come to somebody and say, can you do this calculation for me? There's no motivation for them to do it. Right? Because it's not their career. So doing both for yourself has become very important. And then the balance between theory and experiment really fluctuates depending on people, depending on the problem, depending on the results. So right now, if you look at my group, it's 70% experiment because they are driving everything. Every time we do an experiment, we find a new unexpected phenomenon. And so it turns out the theory people are following along at the moment. They're not driving anything. And the machine learning, for example, is the first time that theory has taken a lead in my group in the last 10 years. Okay. So it really, I mean, it's a very organic formula. You just have to do it and let it guide you where it takes you.
Okay, thank you.
Sure.
Sanant, what we'll do is we'll formally close the session.
Sure.
So I think we start tomorrow at 9 o'clock for the second day of e-SMYIM. So please do join us maybe a few minutes earlier so that we can start on time. So we formally close. Anybody who wants to have a chat with Sanat can stay back. Again, of course, depends on if Sanat has time now.
Oh, no, I'm fine. I mean, it's early in the morning for me, so I'm perfectly happy.
You don't want to